our participants to be introduced to the other faculty uh, participants. So I welcome Dr. Srinivasa Chalapati to our FDP program. So, Dr. Srinivasa Chalapati holds a bachelor's degree in mechanical engineering from Karnataka University, Dharwad. He completed his MTech in production engineering from VTU, Karnataka. He earned his PhD from KL, deemed to be University, Andhra Pradesh. He has over 20 years of teaching experience along with 3 years of industrial experience as well. His research on automobile exhaust pollution control resulted in an Indian patent for catalytic converter technology. He received the Best Researcher Award in 2021 from Novel Research Academy, Pondicherry. He has published more than 20 research papers in reputed national and international journals and conferences. He is the co-author of two textbooks, that is, one on intellectual property rights and the other is on robotics and automation. He served as a member of Board of Studies for the academic year 2005 to 2015 to 2017 for mechanical engineering at JNTU Hyderabad, contributing to UG and PG curriculum development. Currently, he is the Associate Dean, School of Engineering and Head Department of Mechanical Engineering at Anurag University, Hyderabad. Thank you so much, sir, for being part of this FDP. I
Thank
welcome
you.
you to wholeheartedly, sir. Thank you. Over to you, sir.
Thank you, sir. Thank you, Deepak Singh, sir, for the warm introduction about myself. And I welcome all the participants for the wonderful FDP of AICTE, that is ATAL FDP, on shaping the future of manufacturing with 3D printing technologies or techniques, offered by this wonderful SPC Pune. Now, Mumbai. Now, I would like to introduce today's resource person, Mr. Raunak Timble, who is the senior manager at Wipro 3D, having a vast 17 years of experience in additive manufacturing and technology development and advanced production engineering. He has a strong expertise in laser powder bed fusion, that is LPBF manufacturing strategy development, feasibility studies, and creating value chains for complex engineering applications. His work includes technology development, customer engagement, proposal writing, and execution of R&D projects, especially in government-funded innovation programs. He has previously contributed as a lead additive manufacturing engineer at Veron Technologies and as a process and methods engineer at Creative Tools and Components Private Limited. Having such a wonderful experience, he played a key role at Society for Innovations and Entrepreneurship in supporting innovation and knowledge-based entrepreneurship. He holds a master degree in additive manufacturing and advanced manufacturing technologies from the University of Sheffield and a bachelor's degree in mechanical engineering from Savitribai Phule Pune University. His passion lies in innovation in medical devices, solving complex engineering problems through advanced manufacturing, and collaborating with academia and industry partners. We are pleased to welcome you, Mr. Raunak Timble, sir, to the 1 week FDP on shaping the features of manufacturing with the 3D printing techniques. Thank you, sir, and we welcome you.
Thank you so much, sir, for the warm introduction. Just to correct you, I was working with Wipro 3D. I'm not associated with them anymore.
No, okay.
But that's fine. But apart from that, everything was on point. And thank you so much for giving me the opportunity to speak. In fact, when I mentioned this to my father that I'm going to be talking with faculty members from Sardar Patel College, he got a bit nostalgic because he is a graduate from Mumbai University as well. So in a way, it's sort of him giving back to all the faculty members that sort of molded his engineering, sort of base. So yeah, I will just start sharing my screen shortly. So yeah, is my screen visible? Am I audible?
Yeah, yeah, sir. You're
Yes,
audible,
sir.
visible, sir. Please continue.
Perfect. Perfect. So yeah, today I'll be talking. Dr. Kiran had reached out to me, and we had spoken about, how in my current role I've sort of stepped away from additive manufacturing. But I do work with additive manufacturing, in certain projects. But my active role is mainly in traditional machining or traditional manufacturing. So, the topic that I'm going to be talking about is going to be loosely based on my experiences with both of these technologies and how they can come together in giving us the best results when it comes to certain components. So yeah, currently I am part of Creative Tools and Components. As you might have seen, I was linked with them earlier as well. It's actually a family business. So before I went to Sheffield, I worked with the family business for a couple of years, because there were, right after graduation, I worked. Yeah, that's fine. So I was working with them before my graduation, in my masters in Sheffield, and after working for a couple of years in additive manufacturing, I decided to come back and join the family business. So yeah, I'll just briefly talk about our company first. Then I will go into the, what is additive manufacturing. I will cover what I call as the design themes in additive manufacturing, certain design rules that we need to be mindful of. Of course, all of this will kind of come together as I explain. Since much of the faculty members are like in part of this session, I decided to even include one bit of my research element and the kind of research themes which are currently, wherein the research is focused in additive manufacturing. And then, of course, the main basis of the presentation, which is how does additive manufacturing and traditional manufacturing come together. And I'll talk about, with the help of a few case studies from Indian as well as the global landscape. So yeah, just to give you a brief introduction of our company. So this image that you see in front of you is of one of our units. We are based in Pune, so not too far from Mumbai, and we mainly specialize in machining technologies. So you must be aware of the VMCs, vertical machining centers, CNCs. So we house pretty much every machining center, you name it. We have the turn mills, we have 5 axis machines, we have wire cutting machines. So anything and everything related to machining, we have it in house at our end. And our specialty or our USP lies in precision machining. So we are, mainly catering to customers in automotive segment, in oil and gas, in process tooling, process engineering industries. And a couple of years back, we ventured into the medical vertical as well. So in medical, our main focus is manufacturing of the implants and the instruments that are used in the hospitals and operation theaters. So as you can see, these are our 3 directors, and my father is one of the directors, and I joined them about 4 years back. And as you can see on your right, that's kind of like a basic hierarchy, and we are a team of about 150 odd people, at Creative Tools. So yeah, this venture was started about 3 decades back by the 3 directors, as I mentioned, and much of our sales is export driven today. Uh, uh, Mainly, our domestic customers are the companies who have a presence in India, like, as a distribution office. So Halliburton, Alfa Laval, Cummins happen to be some of our biggest, like our main prime customers, and we deal with their plants in Malaysia, in Singapore, in Sweden, in Poland, in the Americas, and Germany. So again, mainly export driven, and we cater to their India plants as well. And yeah, just because I come from the medical sector, this is just to sort of give a glimpse, a sort of deeper glimpse into that. Like I said, about a couple of years back, we started this vertical dedicated for medical implant and instrument manufacturing. And today, yeah, we have customers in India as well as the US. And being a medical manufacturing brings in certain regulations and certifications. And uh, last year, we had gone in for a US FDA as well, which allows us to cater to customers in the US. So before I talk about additive manufacturing, I just want to sort of create the base for traditional manufacturing. What I mean by traditional manufacturing is the CNC machines. Manufacturing has come a long way since the industrial age. You had, very manually driven machines, and today almost everything is computer controlled. So your the operator skill level has changed from perhaps maybe 5 or 6 decades ago to where it is today, because so much of focus has gone into automation and improvement in cycle time, improvement in processes. So these are a couple of the parts that we do using bar stock material. So essentially, you have a slab of material, or you have a casting of some sorts, and you machine it as per the geometry and the design that says on the drawing, right? So these are a couple of the so on your left is the implants that you see over here, and this is a type of instrument that we manufacture and supply to hospitals. It's used in the hip reconstruction in surgeries, and these are trauma related. So in case you have a fracture in certain parts, so if the if the bandage is not going to be sufficient, and if you're going to require some screws and plates, quite often you require these, and we manufacture them at our end. And again, these very small parts, again, a lot of precision has gone into it. These are mainly for the craniomaxillofacial section. Again, we are being able to do that with the traditional manufacturing route, which is you have a raw material of a certain size. You start from maybe 6 and then you machine it down to 1 2 depending on the part size, right? So this is how this is sort of prevalent in today's scenario, wherein when you think of manufacturing, the first thought goes to, well, it's going to be getting done by machining, or in case of polymers, you have injection molding, wherein you are making lakhs and lakhs of parts every day with a mold and a die. And again, just to impress upon the kind of case studies that we have done at our end using machining technologies, a couple of dental implants that we have developed on behalf of certain companies. So we became technology partners over there. Again, much of what you see here is using the CNC machines that we have at our disposal, right, at our end. So a lot of it, when I say traditional manufacturing, I'm talking about subtractive manufacturing when I compare it to additive manufacturing, right? So additive manufacturing now, moving on to this, right? Additive manufacturing is more commonly known as 3D printing. Images that you see on your right, the same part can be printed in a very, very intricate manner. You have the flexibility around making extremely complex shapes, and the principle is very simple, wherein it's a layer by layer addition of material, and this material can be in the form of powder and wires. And yeah, like I said, as the images show, you get a lot of benefits, right? You have the ability to make very complex geometries. Essentially, it's done using a tool without tools. There are certain tools involved, which I will cover in the coming slides, but traditionally, comparing it to subtractive manufacturing, the amount of tools inventory that you require is much less, and you have the ability to bring components to reality in a very fast manner, like a very complete in a very sort of very quick turnaround time. A reduced lead time is one of the obvious benefits of additive manufacturing, because uh, you can have the part design and start manufacturing it right away without having to think about, well, how do I plan for this in a subtractive manufacturing route, because you require fixturing, you require tooling when you are thinking about subtractive manufacturing. So this is the general flow in additive manufacturing, which I'm sure the team, the audience members must be aware of. But I will just cover it in sort of as a glimpse. So you have the CAD file, you export it in the STL format, which is like a step file. You convert it to a triangulated format, so it approximate every surface in triangle voxels, and then you try to fix the errors, because sometimes the surfaces that get created using STL triangles, they are not 100% accurate, so you need to fix those errors. Once you're done with that, you have to slice the part, so you have to define the layer thickness by which the part is going to get manufactured. Nowadays, all of these functions, these three functions, get taken care of by a single software. Most commonly known software in the market is Magix. Quantium is another software which is sort of resource of Renishaw, which is one of the machine manufacturers. Once you have prepared this data, then you can go ahead with additive manufacturing. The machine does the work for you, and if required, there are post processing operations which we'll be talking about in detail in today's session. And yeah, I mean, when I interact with people in the industry, I often meet people who are thinking about it from completely opposite ends of the spectrum. People come and tell me that, well, additive manufacturing is suited only for prototyping. And then the next person that I meet tells me that, well, it's going to replace traditional manufacturing or subtractive manufacturing completely, and any part and every part should and can be 3D printed. When the actual real scope of additive lies right in between, right? It's not just suited for a prototyping. You can get part properties just as good as what you get from castings or bar stock machining. Uh, you can think about ways in which you can increase the quantities and make it commercially viable in batch and lots. But that being said, not every part should be 3D printed, right? And we will be covering this in detail in the next couple of slides. Just to give you a brief glimpse of the kind of technologies that are out there, and every day there are some new technology which keeps coming up, but broadly speaking, these are the techniques that are available in the market today. Our focus today will be on metals, because that is my background and I feel that is much more exciting compared to polymers. Metal additive manufacturing comes with a lot of intricacies and a lot of challenges compared to polymers. So in metals, mainly you have the powder bed fusion, you have direct energy deposition, and a material extrusion. Right. So in these three techniques, as you can see, with the direct energy deposition, you have uh, kind of like an energy source wherein it's melting or sintering the feedstock, which is getting deposited or blown over. And usually you have an existing part or a substrate. So primarily this is used in oil and gas kind of components, wherein a certain section, it's a huge part, maybe 1 meter by 1 meter, and maybe there is some crack which is developed in a certain section, and you just want to add some material there. So direct energy deposition might be the way over there, because it's just about retrofitting the part for usage, right? And raw material is usually in the form of a wire and powder. And this is again very compatible with hybrid manufacturing, because you're probably dealing with very big size parts. You're dealing with, as I mentioned, one example is the oil and gas parts, deep hole drilling equipment, and it's not very convenient to get parts in stock at times when in offsites wherein you're dealing with a lot of deep hole drilling. So many a times these companies like Shell and basically the oil guys who are into oil drilling and petroleum extraction, they have this kind of setup at their end wherein they are able to retrofit their parts in which and it does not disrupt with their supply chain. With material extrusion, so you have this is very much linked to fused deposition modeling, wherein you extrude that material from a nozzle. you have the binder and the actual material getting extruded from that nozzle. Once you build the part, then you debind it, you get rid of the binder and you sinter it. So in that way, the at the end you only end up with the metal part, right? And you get rid of the binder, and you sort of, the raw material is in the form of the material wire, and the binder acts as a support material. So it's material extrusion and then getting rid of the binder, and then there is some shrinkage involved in that component, which you have to take allowances for when you're building the part with the binder. And the technology that we'll be looking at in detail in today's session, which is the powder bed fusion, wherein I'm sure much of the audience members must have seen these machines on YouTube or online, wherein you have a powder bed, and the laser source or an energy source is incident on the powder particles, and the part gets built layer by layer. So uh, as you can see from the images, with the direct energy deposition, there's some flexibility in terms of the axes in how the material gets deposited. In powder bed fusion, it's usually in the z axis, right? That's how the material gets deposited. So in today's scenario, 70% of the additive manufacturing market is occupied by powder bed fusion processes. And why is that? Well, this was the first way which was discovered by Mr. Langer, who is pretty much known as the father of metal additive manufacturing. They came up with this company called EOS, which is one of the biggest metal AM machine manufacturers in today's market. In fact, it's one of the most available machines in India as well, with all our service providers. And yeah, I mean, it has evolved over time, this technology, and it has always been in a state of continuous improvement, decreasing machine costs, so it makes businesses are able to generate a business case for it. These parameters, machines come with open parameters, so you can tinker around with the materials and the properties, uh, and just about get a lot of positive results with these components. You are not You are able to get the maximum out of this technology, of additive manufacturing using powder bed fusion technologies. And again, in powder bed fusion, it can be classified into three types. You have direct metal laser sintering, you have electron beam melting, and binder jetting. So this is powder bed fusion. The principle is the same. I will just play a video so that you will be able to understand it. So as you can see, the laser is melting the powder particles. So as per that particular slice or that geometry, the laser is acting upon that region itself, and the remaining region is not getting affected. Then you have the recoater that deposits a fresh layer of powder, and then the laser acts again. So and during this time, the bed is lowered by a layer. So the recoating and the lowering of the bed is simultaneous, right? And that's how you save on time. That's how the technology has evolved over time, right? So you can see it from the graph on your left. You have the material feed, you add the layer of material, then the laser sinters as per that slice or as per that geometry which is there in that layer. Then you have the movement of the piston, wherein the bed gets lowered by a layer. You deposit a fresh layer of powder, and then again the same steps follow. And at the end, you have the part removal. So once you're done with the complete part manufacturing, that's when you remove the part. And all these three technologies work in the same principle, wherein you have the powder bed, you have an energy source acting on it, and you get the component essentially layer by layer. So the main difference between DMLS, direct metal as a sintering, and electron beam melting is the energy source. In DMLS, you have a ytterbium source laser. In electron beam, you have a cathode source, which is emitting that electron beam, and this electron beam is very, very powerful, very high power voltage beam. So it's much more diffuse, a much more niche compared to direct metal laser sintering. We'll be covering these applications in the next couple of slides. One thing I would like to point out is that this gets done in an inert gas chamber. The reason for that is you're dealing with intense beams, intense lasers, and you're dealing with powders. What's going to happen when you don't have an inert gas? There is a possibility of explosion. So this inert gas makes sure that the processing gets done in a very controlled environment. Because when you're working with materials like titanium, Inconels, nickel alloys, nickel superalloys, it's very difficult to do these processes without an inert gas. Uh, it's very much like how you do the TIG and the MIG welding processes. Many a times these welders will require, they will put in an inert gas, as a supply. So this is the same basis over here, except it's much more potent here because you're dealing with very fine powders and very intense laser beams. Now that I've covered the the technologies, broadly, I would like to shift to the design themes and additive manufacturing. So there are three strategies broadly that you can use or follow when you're dealing with additive manufacturing. You can replicate for additive manufacturing, you can adapt for additive manufacturing, and you can design for additive manufacturing. So, and as you can see from the graphic, form, fit, function. These are the three F's when you're dealing with designing of component, right? So when you are replicating for AM, you are only looking at it as a process change, right? When you're looking at adapt for AM, you're thinking about the process as well as altering the form to some extent. When you're thinking about design for AM, that's when you get the complete freedom. And what do I mean by that? Let's find out. So replicate for AM. This in this strategy, you are not doing anything apart from the same component which you manufacture using conventional or traditional or subtractive manufacturing. You are simply manufacturing the same thing, the same design. The reason for that is this allows the companies or the product users to compare the results and set the benchmark. So essentially prototyping, before you go into producing something on a mass level, you want to develop some prototypes, you want to do some testing, you want to make sure that it does not fail in the meeting the functionalities, right? So this is the primary reason where replicate for additive manufacturing can come in handy. And also, as I mentioned, briefly, wherein certain industries, wherein certain parts they break down. So what do you do? Traditionally, this part was built using castings or forgings or machining, and having this part, there's a possibility that you may not have this part in stock at your end. So what do you do in that case? Well, excuse me, you come up with the same design. You manufacture or you 3D print the same component in the same manner, and you get the same results, right? And then it becomes a one-off case wherein you're not essentially building a business case, you're just making samples or prototypes, and that is where replicate for additive manufacturing comes in. Then one layer beyond that is adapting for additive manufacturing, and this is where you start to get some flexibility in changing the geometry or the material even. So this is a classic case that you see in front of you. This is actually a block manifold. Now conventionally, you will start with a huge block of material, and you will only have these holes wherein you're actually gonna get the fluid flow wherever it's required. But do you really need it? No, you don't require that excess material. So it's about trimming the fat, wherein you keep the same inlets and outlets, but you remove the non-essential material. So it will end up doing the same thing functionally, but you will end up saving on material, you will end up reducing the weight, which is critical for certain industries, which we'll be looking at in a couple of slides. You don't really need to come up with very like no need to do a lot of simulation studies or extensive generative design softwares to come up with these designs. It's just about understanding what is required for meeting the functionality and just changing the form to suit that functionality and not changing it in any way. This again, when we are 3D printing something like this, it also helps in reducing the post processing, the build time. Because additive manufacturing, the main component or the costing or the expense comes from how much time it's going to need for building it. So all these steps, like following this strategy, allows you to reap some benefits of additive manufacturing. And this is where uh, the potential of additive manufacturing gets unleashed, wherein you come up with a completely out of the box thinking. This is where design for AM comes in. And as you can see on the image on your right, just a complete novel heat exchanger. Just to go back a couple of slides, this is a heat exchanger, and then this is essentially a heat exchanger which does pretty much the same thing, right? So look at the difference in the designs. As you can see, this part cannot be manufactured using castings or forgings. This part can only be made using additive manufacturing, and that is where you will able to see the maximum benefits out of this technology. You look at the form fit function, and you try to come up with the best way on reaping the maximum benefits. Like you look at the component or the redesign in such a way that I want to address the maximum benefits out of this technology. And when you design something for additive manufacturing, that's when you're going to get the most out of that technology. So I hope this is an interactive session, because I have a question for the audience members. The image that you see in front of you is actually a bottle opener. Again, very intricate design. Uh, it's in stainless steels. I was actually involved in making this project for a company in the UK. Uh, yeah, and this is kind of like the finished part that you see in front of you. I'm sure, like you must have seen bottle openers. So, which design theme do you think is followed here? You can probably mention in the chat box, and maybe someone can just help me out with their responses. Anyone?
Participants, please participate.
Yeah, sir, somebody has
Participate.
written in the chat box ADM. Sogata Banerjee is writing ADM. Participants, please participate.
Okay. Uh, Anyone else?
Yeah, sir, there is
Adaptive design.
yeah,
Yes.
in chat box there is message adaptive design mode maybe.
Okay.
Yeah.
Can anyone explain why they think it's adaptive and not design?
T Niranjanji, you can unmute yourself and have a talk. Somebody is saying DFAM, sir.
Mm-hmm. Okay. Then in that case, I will ask the same question. Why is it DFAM? Anyone? Okay, so the answer is DFAM, and because, as you can see, this design of the bottle opener, it's nothing like you might have seen before, right? You are, uh, it's definitely not replicate for AM, because you're looking at serial production here. You're looking at least 50 to 100 units, right, in one build. So definitely not built for prototyping wherein you're just making 5 or 10. This is a very organic design, and organic design goes hand in hand with DFAM. In ADAT for AM, it's not a very organic design. It's mainly about just trimming the fat, right? You keep the functionality in the same way. If you can imagine a bottle opener, it will have the same kind of notch, but maybe you might reduce some weight at the handle section, something like that. So that can be wherein ADAT for AM comes in. But something like this, wherein you're looking at the design and you're just thinking, wow, how else can I make this? I can't make this with castings or forgings. That's where DFAM, like whenever you look at any part which is having such an organic shape, that's when you can think, okay, maybe they've gone in for DFAM here. So I'll just cover a couple of the design rules in additive manufacturing, right? So these are very fundamental rules that usually go in adapt for AM, but you can even apply them in design for AM. We are not going to be covering a whole lot of them because, of course, of the time constraints, and you actually require very top of the line softwares to think about things in, from a design for AM perspective. But these are just a couple of things that you should be mindful of. When you're dealing with metal additive manufacturing in the powder bed fusion technologies, in any of them, you are dealing with supports and overhangs. What I mean by that, so you see this image over here. This part is getting printed here, and it's gotten printed here on a bed. And the way it is anchored to that bed in these sections are the support materials. Now, these supports are waste material. You can't do without them, especially when you are dealing with a component of this cross section. You have to anchor it, because one way is the anchoring bit, and if you look at it from a process and a metallurgical point of view, you are diffusing a lot of energy into the powder bed, and it is getting rapidly cooled into the layer, right? So you're melting the particles, the powder particles, and it gets built into a layer. So there is a rapid heating and cooling acting over here. When that happens, you get residual stresses build up, and one way to relieve them is to generate this support material, because if you don't, it's going to start warping, right? So it's going to start warping, and then you're going to get a bend in the component. So this is a must, it's a necessity, and they do add extra cost to the build, right? Because you need to remove them. They are not part of the actual component, but it's just part of how you need to do when you're processing them. So one way to design your components for AM is to have minimum supports and minimum overhangs. And we're going to see some excellent case studies wherein components were redesigned for AM in such a way that these supports and overhangs were almost minimized. So one easy trick to do this is that you can sort of generate this at an angle. So you can add some machining allowance here. If it's not too critical, this feature, if it's not too critical, you can just create an angle over here. So any angle which is more than 45 to 50 degrees, it can support on its own. If it is critical, then you can maybe just create this feature and add some machining allowance here, so that you can end up with something like this. And one nifty way to do this is you can just orient the part like this. So automatically, instead of this, you're still adding material here. you can just tilt your part in such a way that the supports that you see over here, they get minimized over here. So all these things, they make a difference when you're processing this part. The cost of manufacturing something like this is less compared to when you're making this. So you have to make a trade-off, right? If you have to make this part with 3D printing, whether I should go with this or whether I should go with this. So depending on the component and the kind of processes that are going to be followed after 3D printing, that's when you will have to decide, well, maybe I can go with this, and in certain situations maybe you can go with this, the other one. That is, I'll just use a laser pointer. Oops, sorry. Yes. So you can make the same part using this or this. It just depends from part to part, and the process dealings. Ultimately, we want to make things in the least possible cost. So when you're dealing with holes, right, what happens is, again, you need to have the supports because this becomes an overhang. So holes which are less than 10 you can do without supports, but you end up with something like this. It's not a very smooth surface. So as a practice, sometimes you do add supports for holes which are about 5 as well. When you're dealing with holes maybe 1 or 2 you are not going to require those support structures. But definitely when it goes beyond 10 you're going to see a lot, like a change in this cross section entirely. You're going to see some pitting happening over there, and that's not ideal. This can lead to a failure in the build prematurely, just like that. It can collapse if you don't add the support structures over here. So one way to address this is to create geometries like these. These are self-supporting, so oval, elliptical, these sort of like these square, rhombus cross sections. These are self-supporting, and you can 3D print it in this manner. And if you want to retain that circle, then you can bring it about in machining. This is going to save you a lot of time, and it's going to save you material in 3D printing as well, because you will be assured that the process or the build will not fail during the printing process. When you have the possibility of making hollow cross sections, right? And since you're dealing with powders, it should not happen that you make a completely closed hollow part. You need to add an escape hole for removal of the entrapped powders. And as you might have guessed, with the kind of features that you can do with 3D printing or metal AM, you can go up to 0.3 Now this is wherein DMLS comes into the picture. This figure for electron beam melting goes at least like 1 So when you're dealing with very thin lattices, thin features, that's where DMLS comes in, because you're dealing with the powders and the lasers, right? And laser is much fine compared to the electron beam. Very much similar to our castings and forgings. Wherever you get sharp cross sections, you add fillets, and this just helps in relieving the residual stresses which get built up during the building process. Whenever you're dealing with any machining or castings and forgings, the first thing is that they say is, boss, I don't want sharp edges on my parts. I want them buffed out, or I want them rounded off. Same principle here. And even this plays a role in the functionality as well, because you don't want sharp cross sections or sudden changes in the geometries. You want, as much as possible, you want a gradual change in the design. And the image on your right that you see over here is a lattice structure. Again, this is where you must have seen this getting incorporated in a lot of the designs or a lot of the parts that are getting manufactured using additive manufacturing. This feature that you see, you can't simply incorporate that using the traditional manufacturing or subtractive manufacturing route. This is where you start to go closer and closer for a design for AM, right? So, before I go to the next topic, are there any questions, any queries, anything I need to go over again up till now?
Yes, sir.
Yeah.
So regarding the orientation decision, so it will be assisted by the softwares provided like Magix, or as an engineer we have to take a decision on that.
It's a very good question. A bit of both, I would say, because Magix will not tell you that how my part is going to function. Say hypothetically that this face over here, like I'm just giving you an example here. This face is not very critical. Then I can go with this orientation because support removal will leave some marks on that face, and I can just buff it out. But hypothetically, if all of these faces are very critical from a surface finish point of view or from a dimensional point of view, I'm better off going with this because I can make this and then machine it out as per the tolerances, as per the dimensions, right?
Okay.
So Magix is not going to tell you that. That's where you as an engineer will have to come in and tell Magix that this is how I want it. Magix will only tell you that will give you alternatives, but it's up to you to choose which one is most suitable for your component, and that will differ from part to part.
Okay. Yeah. Thanks. One more question on that one.
Yeah.
So the software will provide the how much support material will needed for different orientation or configuration.
Yeah, absolutely. The software helps you out in that. It determines how much time is going to be taken to build the part, what are the number of layers. It's going to even show you whether there are any issues in certain layers. The software is sort of uh, with each passing year, there are improvements in the software which ensures that your build failure rate comes down. Because trust me, in metal additive manufacturing, very rarely have I got it first time right in my experience. Even with all the softwares, access to everything, something or the other goes wrong. So the software definitely have come a long way since when I started working in this industry. And today, like yeah, to a great extent, the softwares are able to help you out in giving you the best results. But of course, like I said, you need to be involved in deciding the orientation of the component.
Okay. Yeah, thank you.
Yeah, any other questions relating to designing, any design principles?
Participants, please unmute yourself and ask if you have any question.
Or you can even put it up in the chat box. I don't mind waiting for a couple of minutes. If not, maybe we can cover them at the end of the session as well. No problem.
Yes, sir.
Yeah. So since much of the audience is from the faculty side, so I've introduced this like research teams in additive manufacturing. So design for additive manufacturing is a very eye-catching and interesting field, but there is also this scope in working in the research side of it, is particularly from the material development, right? And this was where my master's MSc thesis came into the picture. So it's actually based on my experience in working on the R&D side of this. So my project was to work with this material called gamma titanium aluminides, and the way I went about it was EBM processing, because like the laser machines are not best suited for this. uh, what is commercially available today for this material is been done with this, and it's a patented technology by a company in Italy. So the challenge was to try and replicate that, right? And our project was based in the UK. So a lot of when I was involved in this project, a lot of countries were kind of coming together and trying to work with this material. And from the UK, it was our team. So I was part of that team and trying to prove this material out using this additive manufacturing process. The pull was primarily the aerospace industry. Why? Because in a lot of the heat resistant applications, wherein a lot of components getting exposed to a lot of heats, Inconel is the go-to material, right? But the problem with Inconel is very heavy. So titanium aluminides have half the density of Inconel, and more or less the similar properties when it comes to dealing with high temperatures. But there are certain drawbacks and a lot of issues in processing this material using conventional technologies. You just can't, because it's very prone to cracking with extrusion, with forgings, with castings. Very, very difficult to process this material, which is why the focus of this project was EBM processing. So as I covered, impossible almost to process this material using these technologies, and that's where additive manufacturing can create a space on its own, like not just on the design side of it, but you can try and identify materials as well, which are only suited for additive manufacturing. And there are a couple of challenges in the additive manufacturing. A couple of people have tried, keep trying, of course, because even today commercially not a lot of applications with this material. But when that happens, definitely you will see this material a lot more in the aerospace industry. And yeah, this was the machine which was stationed in the research center in the UK. And I was working with one of the engineers over there who was sort of operating the machine, and we were taking our trials in building the test specimens. So as you can see, this is the test specimens over there. So yeah, the summary of it was we were not entirely successful, but the idea was it was a year, like multiple year project. So I was in year one. Last I heard, they had some commercial progress with one of the components, but that was all it went to. Like, and even the companies and the government, because it was a government funded project over there, even they lost some interest in that after a point. But it was a very interesting learning exercise for me, because uh, you can think about this technology in trying to process very difficult materials, right? So tungsten, again, refractory applications, nuclear reactors, different novel materials. So this is again one of my mentors, Dr. Ian Todd. He worked on this material, something which, for biomedical applications, not commercially available today, but it had certain benefits compared to the commercially available titanium Ti6Al4V. So a lot of interest in material development lies in the fact that additive manufacturing can bring it to reality. What may not be possible with castings and forgings, processing certain materials, you can do that with additive manufacturing. And my professor was also working on this novel technique of diode area melting. So this is a snippet of that. So instead of one laser or multiple laser incident on the powder bed, you have an array of at least 100 beams incident on the powder bed. And what from state of what you can imagine is it's going to be a much faster process, right? So of course you'll need to tinker around with the intensity of the beams, uh, much to figure out over there. But just uh, when you look at the technology, all of these things are possible, right? So design for aim is one side of it, but process, coming up with novel processes and novel materials, can also be a research team and a field wherein researchers or academicians can focus themselves. Like a lot of these schemes have come up with the DST, wherein you submit the proposals, right? So in additive manufacturing, you can think about whole host of ideas, and I'll be happy to help any of the academicians and faculty members or students if they are interested in these things. Maybe even after the call, even after this lecture, we can even connect. Interest in support fee printing as well. Again, I will not go too much into depth of this as to how they are achieving that, but there is interest there, because as you can see, adding supports to the parts, not always ideal, right? So how maybe you can do printing without supports, So a lot of research focused in this area as well. And lastly, of course, application oriented, because the industry, they are mainly interested in the applications. Well, if my design or if my component weighs 1 kg today, if I can bring it down to 0.5 kgs, or if I'm able to bring down the price of manufacturing, the cost of manufacturing down, that's going to be application oriented. And the two major adopters of this technology so far have been medical and aerospace. So just to give you a comparison of how traditional manufacturing or machining comes in along in tandem with additive manufacturing. So this is actually the same case study that I've put up for ADAT for AIM, if you remember, because this was not something which was clearly designed for AIM. This was adapted for AIM by trimming the fat, so to speak. So as you can see, this section over here, these are machined. They don't have the same kind of surface roughness that you see on the outside over here. So with 3D printing or additive manufacturing, you are going to get rough surface finishes. And if you are going to need smooth finishes, you are going to need to machine those parts or those features, right? Before that, when you're dealing with making parts on the bed, you're going to have to wire cut them, because you have to part off from the substrate. Sometimes you have to stress relieve the parts, because even with adding the supports, you're going to have some residual stresses. Again, in critical applications, stress relieving is a must. So you rarely can use as 3D printed part for aerospace or medical applications. Stress relieving is a must over there. Maybe only by prototyping you can get by without doing stress relieving. As I showed you here, machining critical features, you need to bring in like conventional manufacturing or traditional manufacturing, subtractive manufacturing, that is, because of the surface roughness constraint. Because with powders and lasers, with the powder size distribution is in the range of like 20 to 30 microns, and in smooth surface finishes, you're dealing with 1.6 microns RA, right? So you need to machine them out. Sometimes you need to bring in polishing, bead blasting, abrasive flow machining as well for certain, internal sections wherein powder might have sort of gotten semi-sintered, or excess powder which must have just gotten, stuck somewhere. So you need to bring in abrasive flow machining for certain theoretical applications. And then there are certain exotic processes like hot isostatic pressing, which is not available in India currently, or I think it's available only in one center in India. A very, very niche process, mainly directed for aerospace components, which you'll be seeing in the next couple of slides. Right. So I'll be covering a couple of case studies now in the aerospace segment. Firstly, I'll talk about where Indian companies have worked, and this is a very interesting case study that you see on your left over here. So this is actually a RF antenna component which is deployed on one of the satellites. This project was undertaken by Wipro a couple of years back, Wipro 3D, that is. And I had a good fortune of working with them. Again, not on this project, but I'm very well versed with this project and how they come about it. So the build orientation was from here. Okay. And straight off, what you can imagine is these features self-supporting, because if you can imagine this component built from here, these get built at an angle. And if you remember the principle that we had discussed upon design for AIM, when you incline certain features, you don't need to add support structures. This feature as well at an angle. So if it's getting built like this in this orientation, you're not adding supports on this faces. So essentially, you are going closer and closer for designing for AIM. Of course, there is going to be some element of machining involved, but this is just to show you an example of how you can bring in the functionality, improve upon it, make it more suitable for additive manufacturing by bringing down the support material costs, excess material usage, post-processing costs as well. And this exciting part was made in aluminum alloy, which is a very common. This particular grade is very common in additive manufacturing. This project that you see on your right, it's actually a rocket engine, and this company is Skyroot Aerospace, which has the backing of ISRO today. There are a couple of aerospace startups, and ISRO and the current government of India is really pushing these startups in trying to come up with really novel, designs. So from the outside, this looks very simple, but there are extremely, like, as far as I remember, about 100 different channels on the inside, which I'm not privy to show you, of course. But this was India's first private cryogenic rocket engine, which I believe was operated with using liquid propellants. Again, I don't know much about the specifics of the operation, but they were able to bring about a huge reduction in the weight compared to a conventional design, and all of this is getting built in one unit. So traditionally, the rocket engines were getting welded or braced together. Multiple components were coming together. Maybe they were adding screws or fasteners, and instead you have this in one component, right? And that always helps and benefits the entire assembly or the entire use case of the product. So this again is an aerospace component, Wipro project, which was undertaken on behalf of ISRO, and straight off, as you can see, a lot of machining done on the outside. So definitely not something which was done only with 3D printing. There was machining involved as well. And over here, as you can see, I've just added a zoomed in photo over here. I hope you can see the asperities on the surface over here, right? So these asperities are caused actually by the supports. They are supports which are removed. So support removal leaves certain marks or dents on that face. So if it's not critical from a functionality point of view, we leave it as it is. But this is what happens when you print the part and the supports are added on that face, right? So the idea is to minimize the supports as much as possible, but the intent in this project was to replicate for air. That was the theme which was followed. So the same existing design, which earlier was done with using investment castings, they just went with the same design for 3D printing, which is why they were not able to leverage the maximum out of additive manufacturing. So yeah, this project was personally involved in tooling as well. A lot of companies in India are working with it in this conformal cooling channel. So this component which you see, this is a sort of like a transparent view of the same component. As you can see, very complex channels. You just can't make this with castings or forgings. You can't. So what this does is that it helps in reducing the rejection, because in injection molding, when you're dealing with thin cross section components, which is plastic components, there is a kind of a warpage there, right? And there is shrink marks because of improper cooling cycle and everything. So to compromise for that, usually users, they make the process very slow. So when you work with such channels, such conformal cooling channels, they are sort of adhering to the component in such a way that it brings about a universal cooling effect. So you bring down the rejection as well as the cycle time, because you can work with aggressive parameters for the injection molding cycle. So these features are made possible with additive manufacturing, and the tooling industry is using this for certain critical applications. These intake manifolds, again, it was a prototyping project. These parts designed for conventional manufacturing. So the automotive industry today in India, and rather even at a global level, is not really looking at additive manufacturing from a serial production or mass production point of view. It's mainly from a prototyping, because the components for automotive, usually the industry is set in such a way that you get it done with castings and forgings, and the imperative for that industry, or the mandate for that industry, is that it should not uh, it should not it should function the way it is. And the industry is very comfortable with castings and forging technology, right? But again, with prototyping, you are able to untap different benefits, so you can try out multiple iterations in the same build. The quick turnaround time, so you don't have to wait a lot of time to develop the fixtures, bring in the tools. Within 4 days, when you have the designs, you can manufacture the parts. So yeah, the this is just to show you the perspective of different industries of India and how they are adapting to additive manufacturing. Right. So this is a very interesting component. One of my first builds, wherein this component that is there, this function was into the mixing of certain fluids, and it was doing it with the helical flow, helical sort of trajectory that you can see here. We are able to print feature of 0.15 mm here, and the height roughly was in the range of 30 to 40 mm. So you can imagine like how it was so fragile. Like even holding it, we were afraid that it might break off, and at certain times we even snapped it very easily. So very fragile component. We're able to manufacture it, and this was a serial production item. So we're able to print multiple items in a single build. And yeah, we look at this design, and you go to a machining like a machining shop, they're gonna just scratch their heads on how to machine this component. You're just not going to be able to machine any feature or cast or forge any feature as low as this. Maximum you can go is maybe 3 to 4 mm, and maybe certain cases 2 mm in certain very intricate processing. But additive manufacturing allows you to work with such designs. Right. So medical again is a huge adopter of this technology, and India is very much at the forefront of it. So this is company called Jajal Implants, and Jajal mainly is focusing on developing patient-specific instrumentation. So um what the today's scenario, when you don't have patient-specific implants, you have to rely on off-the-shelf products. So that is off-the-shelf implant and off-the-shelf instrument. Before you place any implant, you need to prepare the bone resections, right? So uh, what Jajal figured out to do is, okay, if making the implant in 3D printing is proving to be expensive, one way to address that is, what if we come up with patient specific instrumentation, right? So these are instruments that you see in front of you. These are essentially cutting guides. So the doctor is able to prepare the bone resections using these as the guides, and they are able to cut the bone accordingly. This is very much in sync with the pre-op planning, because there are softwares available wherein you are able to extract the patient data, the patient CT scan data, and you are then go into the segmentation exercise, and then come up with this very patient specific and an instrument which fits into the the bone or the damaged bone in a very snug manner. The fitment is so perfect that the doctor is able to prepare the bone resections, and then again go and place the implant. And the benefit is just huge here, because if you aid the doctor or the surgeon in accurately cutting the bone resections, it goes a long way in the patient recovery. I'm sure everyone must be knowing someone who has undergone a knee replacement or a hip replacement surgery. So there is a huge possibility of revision surgery, wherein the implant is failed. During the rehab process after the surgery, there's a lot of time gone into the rehab, into rehabilitating the patient, so that they are able to bring in the same sort of motion and movement in their day-to-day life. But sometimes, a very high percentage of times, the implant fails, and they need to go in for revision surgery, and that is the worst case situation for a surgeon. So if uh, anyone is able to help the surgeon in trying to minimize the revision surgery, that is best case situation, best case scenario for them. So these are certain two applications that they have presented, wherein very complex surgeries can be made easy with using these cutting guides. And there's another company called Lucid Implants, which develops implants. Now, right, what you can see over here, neuro, again, very, very critical, right? Somebody is facing brain trauma or a brain tumor of sorts, and certain bone needs to be removed over there. That needs to be replaced with a plate of this sorts. When you look at that geometry, that is fitting that person's anatomy, and that is what 3D printing allows you to do. It allows you to come up with that design which is fitting that particular patient's anatomy, and certain critical surgeries can be performed with fair ease when you develop implants which are suiting that patient's anatomy. In the Indian landscape, much of this effort relating to implants is focused on non-load bearing implants, because the confidence isn't quite there amongst the manufacturing as well as the surgeon community whether you get the same kind of properties. But the onus lies on the manufacturers in trying to develop case studies for that, and slowly but surely we will do that. I'll just show you a case study. This is like a YouTube link. It'll just get redirected over here. This is a case study. So this is the bone resection guide, right, which I covered in the earlier slide. And my question to the people, they're able to see the screen, right?
Yes, sir. Yes, it is visible.
Yeah.
Yeah.
Yeah. So as you can see, this bone resection guide over here, this was the instrument that I was talking about in the previous slide. So they prepared the bone resections with using something which is fitting that patient's anatomy over there. And then you have the implants. Again, these implants are not as 3D printed. As you can see, they are a polished surface. So this is not what you get from 3D printing. So definitely some element of conventional manufacturing has gone into it, mainly from the polishing side of things. So these implants, they come together, then the occlusion of the mandible, and then you place the foci, and then you have the mandible, and that's how the jaw operates, right? So certain cases wherein you need to develop something for a certain patient, right? That's where uh, additive manufacturing can really create interesting case studies. I'm sorry, this link got directed me. Let me just find my presentation again. Yeah. Is my screen visible again?
Yes, sir.
Okay, perfect. So those were a couple of case studies that I covered with from the Indian landscape, and now we look at one of the pioneering aerospace companies, which is SpaceX. So this is again one of their engines, very much similar to Skyroot Aerospace one, and I managed to get an image of one of how their engine looks from the inside. So these complex cooling channels, I mean, you can realize the complexity of how the how this operates as a heat exchanger. Just incredible designs are possible with additive manufacturing. Again, chamber wall thickness is as low as 0.8 to 1.2 mm, and a huge deal of part consolidation. So very much similar to the Skyroot Aerospace case study, wherein You bring in a bunch of parts together in one single component, make use of the technology to build very thin features and bring down the weight. And in the aerospace field, if you're able to bring down the weight of the engine by even like 50 grams, that's a huge implications. It has huge implications in the fuel savings, right? And in the payload carrying capacity and all those things. So just tap a lot into this technology with when you start designing for this technology. That being said, again, abrasive flow machining comes into the picture here, because if you can imagine here, powder must have sintered here, or must have like very small particles. You don't get a very good surface finish, right? So you need to go in for abrasive flow machining. You need to go for a hot isostatic pressing, because with additive manufacturing, you're going to build components which are going to be roughly 98.5 to 99% density. There are going to be small porosities in the component. And when you're dealing with aerospace components, you want to make sure that one, the component is 100% dense, right? So hot isostatic pressing, not easily accessible, but in certain critical applications, a must for things to go perfectly well in the field. Again, aerospace case study, very intricate geometries being made possible over here. So at the front, this looks like this, and the sectional view, I've even added an image over here. So introducing these lattice structures, bringing about significant weight reductions, as you can see here. And just the idea is to go as close as possible to design for aim, because it's very difficult to go and follow design for aim entirely, because something gets fitted into something. So you have to adapt for aim in some ways. You have to bring in the functionality. It will have its restrictions, but the closer you get to design for aim, the more and more benefits you get out of this technology. Now, this is a very, very interesting case study, and of course, I'm sure a lot of people must know of Apple, the most pioneering companies over here in the world. And they reported this case study this year, wherein the Apple Watches, this case is getting 3D printed, and it's being done at a huge scale, because they have reported as of this year they have saved roughly 400 metric tons in raw titanium material, and they're going about it in using recyclable aerospace grade material. So as you may have observed, in additive manufacturing, only a certain area of the bed gets printed. The remaining powder, what happens of it? Well, you can recycle it, you can reuse it, right? And that's what precisely what Apple have done. They have built these, like, this is the array of parts that is getting built, as you can see in this video here. So they're roughly like, this is a multi-laser machine, and there are such machines available in the market, and they're building these parts. So again, these recyclable powders, this component, that's how it gets built, and then this is the end use case. So just an exceptional case study, wherein uh, up until a couple of years back, we always felt like additive manufacturing was suited for serial or batch production, but Apple have managed to bring it to a substantial scale. Just go to the next slide. So the design is intricate in such a way that there are certain thin features over there which are not possible with forgings, and they were able to improve upon the waterproofing process for the antenna housing. So not just weight reduction, but also improvement in the functionality, and that is where additive manufacturing thrives, in identifying cases wherein you think beyond the casting and the forging mindset, and you start thinking about things in the additive manufacturing perspective. So this was a snippet of the build orientation that you see. So the reason why they are built like this, again, this is going back to what I spoke about in design for AM, is minimum support structures. When you incline it in such a way and you anchor it simply over here, you can build this part without support structure. So the simplest of principles, you might be able to see it, in the case studies that I'm presenting to you. And in the medical segment, there's this company which has reported the world's first FDA approved pedicle screw. And as you can see, there are porosities over here, right? And certain lattice structures over here. So their claim is that it's going to permit a better osseointegration. Osseointegration is fusion with the bone, right? So ultimately, an implant needs to interface with the bone, and it needs to allow the bone growth, because many a times you end up removing these screws, or they have a shelf life of their own, right? So your implant should allow for that. And with having these rough textures, uh, their study or their claim is that it's going to give a better bone growth. It's going to mimic the bone topology as well. So again, a whole host of features and ideas possible with additive manufacturing. And this is just a snippet of the kind of parts that we make actually at our end. We have made this component at our end. The only difference is here, cost of manufacturing is not more than $4 US. Over here, the cost of manufacturing can be as high as 100 to 150 US. So the commercial case for this, to like making a commercial case for this, requires that kind of criticality in the surgery. If off the shelf products, if the patient is okay with off the shelf products, and if it's not to a critical surgery, if the doctor is confident that off the shelf products will work for it, definitely go with this. But then there are certain very critical procedures, tumor related procedures, which need to be very focused on patient specific elements. That's where you start thinking about 3D printing. Then the cost implications of it outweigh the functionalities, right? So sorry, the functionalities outweigh the cost implications. My apologies. And there's this pioneering company. So this, in my books, is the number one metal 3D printing company operating in the medical segment, which is Restore 3D. And they are going about in a very aggressive manner and trying to develop products for essentially the whole body. So this, what you see in front of you, is for the total ankle system. So total ankle replacement implants are being manufactured at their end. These are surgical wedges, again, for the total ankle system. So this is a talus implant, again, for the foot region. So all of these are getting manufactured as per the patient's anatomy. Yes, there is an element of standardization, but you get a lot more flexibility, when it comes to 3D printing and trying to bring in a personalization to each person's anatomy. Right. And again, knee implants as well. This is essentially a knee implant, and you know this is completely patient specific knee implant. If you go online and see, probably I should have included a photo here, but this is not how a knee implant looks like. This is a very novel design, and interestingly, their design shows that this is a rough surface here and this is a smooth surface here. So wherever you have contact with the bone, in the medical implant segment, the rough surface finishes can mesh with the bone in a much nicer way that allows the bone growth. And whenever certain element interacts with another element of the implant or the joint, that's where you need a smooth surface. So this component is a blend of 3D printing and polishing it in the right manner, and this is what they have achieved at their end. And this Restore 3D have been able to sell and market 3D printed implants in a huge way. Definitely, uh, the incidence of implants in India is more or less restrictive to the craniotomy implants that I showed you, or the jaw implants that you had seen, the maxillofacial implants. But slowly but surely, maybe we are a decade away wherein we are able to see a personalized hip implant or a knee implant in the Indian market as well. And again, this again, very interesting case study in the athletics department. I had the honor and the privilege of working with this gentleman, Mr. Dimitris, during my time in the UK. This Metron Additive Engineering, and their main focus was working with Olympic level athletes and coming up with bicycles for the UK cycling team. And this gentleman has come up, he was a biker himself, and now he designs bikes for bicyclists. And yeah, I mean, he's been instrumental in the UK cycling team in winning multiple medals in multiple Olympic events. And this is one particular, I love this image. The reason for this is he's been able to stack these parts on top of each other, and you can do this with additive manufacturing. A very unique possibility wherein you're able to bring in serial production as well. Of course, this complicates post processing in a big way, but if you have the size, if the machine size is available, and if you are able to print these parts, why not, right? So a very unique case wherein they've been able to nest these parts together, and now the challenge will be to remove or separate them from one another. So, based on those case studies and what I have covered so far, is that additive manufacturing will not replace conventional manufacturing. It will work in unison. Uh, there are going to be some things which are going to be possible with additive manufacturing. Some things will remain the same when it comes to subtractive manufacturing. Uh, DMLS of all our AIM processes, so the laser-based technology is proven for most applications because uh, when you think about lattice structures, weight reduction, topology optimization, all these boxes get ticked when you work with laser-based systems. And design for additive manufacturing knowledge critical to harness the maximum benefit. So the ideology is, if you design a part for castings, for forging, and think about 3D printing it, you're only restricting yourself for replicating for you. But you can think about moving beyond that and try and build a business case, much like Apple did. Like, that was so impressive because they have been able to do it at scale. And surely the trend is that, more and more applications will be realized wherein additive manufacturing will be able to be performed at scale. But subtractive manufacturing is here to stay, because not everything is possible with additive manufacturing. And that concludes my presentation. You've been very patient, and yeah, I am open to hearing any questions. I think we have a couple of minutes till the next speaker.
Yes, sir. Thank you very much for such a wonderful session. Participants, you can unmute yourself and ask questions. Hello, participants. You can unmute yourself and ask questions.
Sir, I would like to ask one question.
Yes, tell me.
Sir, in your presentation, you have used a word, replicate for aim. What does it mean, sir? Somewhere.
Yeah, replicate for A means you, like, imagine something wherein you've designed a component for castings or forgings, right? So you keep the same design and you 3D print that part. That is replicate for A. So you don't really tinker around with the design. You just change the process.
Okay.
And that is suited for the prototyping applications, because you're gonna, the part is not 100% design, or it's not closely designed for additive manufacturing. So you're just using the same design and 3D printing. That's it.
Okay, got it, sir. Thank you.
Yeah, is there any other question? Participants, you can unmute yourself and ask.
Sir, one small doubt.
Yes, sir.
How far the metal will become affordable, sir, in a near future? Or
Sir, I mean, as I said, it will mainly be driven by the aerospace and medical segment, sir.
yes, yes.
They will be the main users, and in aerospace and medical, uh, there have been excellent business cases wherein additive manufacturing has come in and kind of replaced conventional or subtractive manufacturing. So, uh, uh, when you look at affordability, you always look at the life cycle of the component, or the assembly, right?
Yes,
So, in its performance, how much am I going to save in terms of, so aerospace segments are relating with the payload, are relating with the fuel consumption, right? So it's a life cycle, and people have been able to create business cases for it. So it's difficult for me to answer that question, because it's happening now to some extent. But that being said, maybe the ratio is 15 to 85%, wherein the adoption of AM is not that much compared to how subtractive manufacturing has
Hollywood.
worked.
Yeah,
But
yeah, yes.
but the idea is that additive manufacturing will identify new applications. It will not. It will be very difficult to replace conventional manufacturing, but it will end up identifying new applications and a new thought process.
Yes, sir. Definitely for the medical applications and all, where some critical kind of joints or designs that need to be done, that can be done with the AM technology very easily.
Yeah,
But
yeah, absolutely.
but still, if we made the same thing by conventional,
Hmm.
the cost of it, that means because overhead cost is more in the additive manufacturing of metal, because the cost of the equipment itself will be around 4 to 5 crores or beyond.
Absolutely. Absolutely, sir. Absolutely. I mean, that's where your one's thought process for designing for additive manufacturing, if that comes in, right?
Yeah,
When you start designing parts for additive manufacturing, then the alternative of using castings or forgings will not be there. And your only way will be to use additive manufacturing. And
yes,
there are benefits to, yeah, even if the initial investment is there, if the life cycle benefits are there, then people will go for it. Of course, in the medical segment, in today's scenario, there is a price capping on implants. The Ayushman Bharat scheme has been launched, to sort of democratize the pricing of all these implants. So 3D printing may not be available for the masses, but instead it can be utilized for only critical surgeries, wherein someone's jaw needs to be replaced, or someone's sort of brain, like the implant, the craniotomy procedure, and all these things. So um, in the US, of course, it is being done at scale, and usually it does seep through in India maybe a couple of years later. But as of now, yeah, I mean, maybe it might be available only in the tier one cities, something like that. Uh, and maybe we are about 7 to 8 years from that, away from that. Yeah,
thank you, sir. Thank you.
yeah.
Hello, sir.
Yes,
Uh,
ma'am.
yeah, sir. Just a question. Like in your summary slide, you mentioned that AM will work in unison and it is not going to replace.
Hmm.
So, how about AM's growth in small scale and medium scale industry? Like, where do you see additive manufacturing there in those industries? Because aerospace and all multinational companies and all fine, but what about small scale and medium scale industries?
Yeah,
Where can
ma'am.
AM find its place there?
Very good question, ma'am. So I have not really covered that in my presentation, so I don't have any reference material for that. But one application for that is inspection fixtures. So sometimes
Okay.
you need to place the components, right, and you need to come up with very complicated inspection fixtures for certain features. So you can 3D print them, because making an inspection fixture or a fixture of any sort is going to require you to come up with a block of material, machine it out, and then you can check it. But what you have the design ready and available, and build that fixture as a one-off part. So inspection fixtures definitely of great use. In fact, we use them at our end.
Okay.
3D printed inspection fixtures, because
Yeah.
they prove to be, in a matter of hours we have that inspection fixture ready at our end. And usually it's in polymer material, because you don't really require a metal inspection fixture.
Okay.
So you can make a sort of a you end up saving some costing there as well, because metal of course becomes expensive.
True. Yeah.
Yeah. So inspection fixture off the top of my head, for small scale
Mm-hmm.
industries, readily use application for that. And
Okay. Okay.
even for prototypes. So there are many startups in different segments who want to just build some prototypes, see how it looks, see how it functions. So for
Mm-hmm.
prototypes also, small scale industries, medium scale industries can make use of that. Again, as Dr. Srinivasan said, the metal machines are very expensive, but you can make headways with the polymer printing machines.
Yeah. Yeah.
Yeah,
Okay.
thank
Thank you,
you,
sir.
sir. Yeah, yeah. So if you have any further questions, sir, we'll email you. You can write it in a chat box, and no, maybe, sir, you will be means, will be now you can connect with Ronak Timble, sir. I will give you his maybe email ID. Okay.
Yeah, I've
Yeah,
just
it's
written
already
it in,
put. Yeah,
yeah.
yeah, yes, sir. Thank you very much, sir, for such a informative session. Uh, uh, eh, so I think our next speaker is also joined. So we'll start next session. Thank you very much, sir, for a wonderful talk here.
Thank you for your time, everyone. Good night. Bye bye.
Thank you, sir.
Yeah, participants will start the next talk.
Hello, Professor Basme. This is
Yeah,
Ajinkya Shetty. Do you want me to go forward or you want to
yes, sir.
quickly
I will
introduce me?
just share the screen
Okay,
now, and a participant will introduce you, and then we'll start the session, sir.
thank you.
Yeah, I welcome Ajinkya Shetty, sir, who will be delivering uh, the next talk in which is a session 10. Okay, so I request one of the participant, Professor Swagata Banerjee, to introduce our speaker. She is he is an assistant professor, Department of Civil Engineering, University of Engineering and Management, Jaipur, and her research interests are structural stabilization techniques, sustainable materials, BIM, and applied AI and IoT. So, Swagata Banerjee, are you there?
Yes, sir. Thank you for the introduction. Am I audible?
Yes, yes, you are audible. Please go ahead.
Okay, thank you, sir. So, let me introduce the speaker for our next session, Mr. Ajinkya Shetty. Mr. Ajinkya Shetty is a product engineer at Altair, USA, with 15 years of experience across engineering software, technical sales, and enterprise technology. He specializes in demonstrating value through modeling and simulation solutions, aligning product capabilities with customer objectives and industry requirements. His expertise spans technical sales, consultative selling, multi year licensing strategies, sales enablement, key account management, and customer success. He has strong capabilities in data driven decision making, using analytics to identify customer needs, competitive gaps, and long-term solution opportunities. Mr. Ajinkya is also a data science and AI enthusiast skilled in Python, machine learning, cloud technologies, and AWS. His technical background includes experience in CAD, application development, mechanical engineering, and delivering proof of concept solutions across industries such as manufacturing, aerospace and defense, consumer electronics, and healthcare. He has worked with leading organizations including Altair, Comsol, Follett Higher Education, and the University of Texas at Arlington. We are pleased to welcome Mr. Ajinkya Shetty to the one-week faculty development program. Over to you, sir.
Thank you,
Yep.
Sogata Banerjee. Thank you very
Thank,
much. Yeah, and his talk is on understanding design thinking approach in 3D printing. Yeah. So I will stop my screen, sir, and then you can share your screen.
yeah, thank you, Dr. Basme, and thank you, Sogata. I'll quickly share my screen and get into today's talk.
Yes, sir.
Do you guys see my screen?
No, sir. Yet it is not visible.
Okay. How about now?
Yes,
Yes,
sir.
sir.
It is.
Okay.
It is there.
And I'm putting it
Just
in a
put it in the
presentation mode.
presentation mode.
Yes.
Yeah. Thank you,
It's
sir.
in presentation mode right now, right?
Yes, sir.
Okay. Sounds good. Thank you. Again, thank you for the warm welcome, and thank you for inviting me for this talk and sharing my experience. My today's talk is going to be on additive revolution from prototypes to production about 3D printing. Before I get into details of this presentation, I would like to introduce myself. So my name is Ajinkya Shetty, and I'm originally from Mumbai, India, currently based in California. My educational background, I have a bachelor's in mechanical engineering from University of Mumbai, graduated in 2012. And then I earned my master's in mechanical engineering, focusing on thermal fluid sciences and MEMS fabrication in 2016 from University of Texas, Arlington. As far as my work experience is concerned, I started my career at Comsol. So back at my grad school, I was exposed to MEMS fabrication and finite element analysis. So I used commercial code for my thesis and did some experimental work in class 100 clean room. So that's where I got my first break in corporate in the US. And I started working for Comsol. Worked there for 6 years and then moved to the West Coast in Los Angeles area, working for Altair Engineering, which is an American corporation. And Altair recently got acquired by Siemens Digital Industry Software. So Altair now is part of Siemens. Today's talk is going to be focused on additive manufacturing and 3D printing. But before we get in, I want to give you guys a quick disclaimer. This presentation reflects my personal views and it is not endorsed by nor it represents the view of my current or past employer. With that, let me quickly go in today's agenda and what we have there. So I'll set up the stage talking about the tech. After that, I will touch upon the history of additive manufacturing and 3D printing. I'll cover the market, then talk about 7 families of additive manufacturing, deep dive into physics. When I say deep dive into physics, I'm not going to talk about equations. but give you a sneak peek into different methods. Then talk about the role of simulation, both physics, AI, and machine learning. And then talk about the startups and titans, mainly in the US market. And then discuss the future from my lens. All right. So the question is, why are we here, right? Why does this matter in the first place? Now, there are three core benefits to additive manufacturing. The first is complexity. Complexity is free, right? So in traditional manufacturing, cutting a complex shape costs more money. There's tooling involved, a lot of research and investment goes into it. However, in printing, a complex lattice costs the same as a solid block, and the printer does not care about how complex the shape is going to be. Second is the digital inventory. Now, instead of paying to store thousands of spare parts in a warehouse, what you basically do is just store digital files and then print it when you need. So it's very agile, very lean, right? And third is weight reduction. Now, here we've taken an example of aerospace, which demands lightweight, light parts, and at the same time, it requires structural integrity, strength as well. And we can remove material from places without making it structurally weak, making it light and more efficient, right? I joined at 6 a.m. here, California time, and I heard one of the speakers, Ronak, talking about aerospace. And there is a lot of application in this area, but then there are new and upcoming areas as well where 3D printing is really shining. Now, talking about, setting a stage here with subtractive CNC, let's say, and additive piece, right? You have to shift your mindset when you talk from traditional subtractive manufacturing, which is like sculpting, to 3D printing, which is you're putting layers of material over a substrate, right? So what subtractive does is it creates a lot of waste, and you can only make shapes your tool can reach. However, additive is the opposite. You start with nothing and add material only when needed. And essentially, it's near zero waste, and gives you total design freedom, like creating complex internal cooling channels, which would be very difficult to drill. Now, this is picture of the UTA Fab Lab, a 3D printing lab, which is based on FDM, the fused deposition modeling. The reason I put this is this was kind of my motivation and my first exposure to 3D printing. And I used 3D printing for my master's research. Again, it was not part of my research, but for my experimental setup, right? While I was designing the setup, I used 3D printing. But just giving you guys a sneak peek of how I first got exposed to FDM and 3D printing. Now, this is the iPhone moment. Now, a lot of industries have their different iPhone moments. Currently, for large language models and AI, ChatGPT is the iPhone moment. Now, up until GE manufactured these fuel nozzles, people thought that additive manufacturing was just for toy projects, right? But when every industry has a turning point, and for 3D printing, it was GE Leap fuel nozzle. Now, before this part, as I mentioned, it was considered as toy. But then when GE took a fuel nozzle, which requires 20 separate welded parts, right? 20 parts, and then printed it, that is subtractive version, but then used additive manufacturing and printed it in a single unit. And that was a game changer. The result was the part was 25 times percent lighter and 55 times more durable. And this was the moment the industry realized that, okay, this is real, right? This is not toy project anymore. I'm going to show you a quick video of like insights into this GE fuel nozzle, and then we will carry out the presentation. Is there sound with the video or?
No, sir. Sound is not there.
Okay, there is no sound. Just give me a moment. Let me see.
Was assigned that.
Yes, it is not.
When I was brought over to this job, they told me you have to come over, design a fuel nozzle that is going to be 15% better fuel burn than what it's replacing. It's going to have 50% NOx margin. And by the way, your customer is expecting a fuel nozzle that lasts forever in the field, basically. And so that's a tall order for such a high technology component.
When Josh Mook was assigned that job in 2011, additive technology had reached a milestone. Developers were telling design engineers like Josh that they could finally use 3D printers for test parts.
We really needed to have a confluence of the right materials with the right type of mechanical properties, and that came into being in 2005 when we started working with a material called cobalt chromium.
Greg Morris is a pioneer in the field, but Josh still had doubts.
I personally was very skeptical, not coming in from an additive background.
This is a process that is very foreign to people initially. You're taking metal powders and you're consolidating those, micro welding those with a laser or an electron beam to create a three-dimensional object layer by layer.
A fuel nozzle has a complex role in a modern jet engine, especially in a lean burn system. Additive technology offered engineers unprecedented freedom to optimize fuel and air mixing.
The secret to designing a good fuel nozzle is proper management of air and fuel. Often I need very complex shapes. I need shapes that a machine tool cannot generate. I need hidden channels or cavities or whatnot that I cannot machine.
Because these technologies are additive in nature and not subtractive, you can create designs that you can't create any other way. For instance, you can put in very complex internal passages, lattice structures, things that you can't cast, things that you can't fabricate, weld, machine. Additive technology brings to the forefront an ability to produce components and parts that you just frankly cannot make any other way outside of additive.
Mark Shaw heads the nozzle design team, the person who would be responsible for delivering an additively manufactured part.
There's always concerns with new technology. And additive manufacturing certainly isn't a mature technology. The material properties are very good. The equipment is pretty reliable and has developed quite a bit through the years, but it's not to the same level of maturity as the subtractive processes. So there certainly were areas of concern.
So the first milestone for me was when we first ran a nozzle that included some pieces made with additive manufacturing in an actual combustion environment, and they survived.
Tests showed those first pieces would hold up and perform well.
Circulating fuel temperature.
The team decided to take things farther.
Okay.
So after that initial test where we said, okay, additive has a chance here, we now said, let's design the best fuel nozzle that we possibly can.
We realized that we could start combining pieces together. And as we combined one piece and two piece, we moved at some point and realized that we have 20 individual pieces here that perhaps we could print them all as one. And that was really the revelation. That was really the turning point in our thinking.
This was a much more complex part, a bigger 3D manufacturing challenge.
There was a period in time where we could not build that using the best that we knew from additive. That was very tense time. I had a lot of senior executives saying, are you sure this is the right thing to do? I had to say, trust me.
So that particular point in time, there were some extremely challenging geometry that were being presented to us. In fact, we had some doubts ourselves as to could we build those components and meet those design criteria.
I got a phone call approximately 2 a.m. in the morning. Never get a phone call at 2 a.m. in engineering. Right. Got a phone call from the manufacturer that said it did it, it completed. I think we can do this. And that was it. That was the entire conversation. I knew at that point that we had it, we could move forward, we were going to make this work.
So great. As you saw, the geometry was extremely complex. It would have needed 20 different parts to be welded. First of all, it's difficult to machine that kind of geometry. And then second of all, you need 20 different parts to weld, right? Instead of that, they came up with this additive design, and which was structurally more durable, at the same time lighter as well, which is need of the hour in that industry, right? So we move to next slide. So let's take a quick look at how we went from lab curiosities to factory floors, right? So it started in 1986 when Hull, the founder of 3D Systems, he invented stereolithography. Basically, he used a UV laser to cure a vat of liquid resin, and then the goal wasn't mass production back then. The goal was rapid prototyping, getting a physical model in your hand overnight instead of waiting weeks for a machine shop. So that was the whole goal. And this is again 1986, right? Long time back. Now in 1989, a few years later, Scott Crumb invented fused deposition modeling, or FDM. And this is what people think of when they think of additive, when they hear the word 3D printing. It is essentially a high-tech hot glue gun, melting plastic filament and drawing shape layer by layer. This became the standard for making functional plastic prototypes, right? The right side, you have the diagram, spool filament, support of spool filament, and then there is this hot, liquid coming out from the printing nozzle, which is printing a layer by layer on that printing bed. Now, this was the explosion moment, right? Around 2009, key patents which existed expired, and this launched the maker movement with companies like MakerBot. There was a huge hype cycle where people thought that everyone would have a printer in their kitchen. That didn't quite happen because printing is actually kind of hard, right? But what this did is it created, or rather skyrocketed, public awareness. It became, extremely ubiquitous. Now that brings us to today. We aren't just prototyping anymore. Big players like HP have entered the game with machines designed to print 10,000 to 100,000 parts. And the conversation has shifted from does it look like part to does it perform like a part? Now, I'm going to put some light on the market and why now, right? What is the need? So the industry is projected to hit nearly $36 billion by 2030. And that is a whooping 17% CAGR. The real driver isn't plastic toys. It is metal printing for high value application in aerospace, of course, but medical and dental fields as well. And I have some examples in our presentation, which I'm going to talk about today. Now, another inflection point was the COVID wake-up call, right? COVID was a massive wake-up call when everything came to standstill, the global shipping froze, and we realized how fragile our supply chains were. Now, with additive manufacturing, which offers distributed manufacturing, if you have a printer and a file, you essentially have a factory. And instead of one mega factory in China, imagine 100 small print farms in 100 different cities, printing parts exactly where they are needed, right? It's like it's like the cloud model, pay as you go, so print as you need. Now, we're also seeing some mass customization here. A great example is Adidas 4D midsole. They print lattice structure that are tuned to a runner's specific weight and stride, and you can't essentially injection mold this piece, right? You have to print it, and this is not, one size fits all, right? It's one size fits one, extremely customized. Now, economically, it comes down to the break-even point. It has to make business sense, right? So molding has high upfront cost for tooling, but cheap per part cost. So it wins at high volume. At the same time, printing has zero upfront cost, but higher per part cost. But right now, printing wins at low to mid volumes. But as printer gets faster, that break even line is moving higher and higher, right? That's what we are seeing now. Now, let's briefly cover the technology itself. There are generally 7 families of additive manufacturing, which I'm going to cover today. First one is VAT polymerization. This uses UV light to turn liquid resin into solid plastic. And it gives you incredible surface finish and details. But the challenge with this is the part can be brittle and degrade in sunlight, right, with UV. The second one is FDM, or material extrusion. Then you have FDM, which is workhorse. It pushes melted plastic through a nozzle, and it is cheap and uses real engineering parts like ABS, nylon, engineering plastic, I mean. But the surface finish isn't great and parts are weaker along the layer lines. The third one is polymers, or PBF, and it's powder bed fusion for polymers. A laser sinters nylon powder. And the cool thing here is that you don't need support structures, because anything which you manufacture via 3D printing or additive manufacturing, it cannot just hang right in air. So you need support structures for that. But with this, you don't need support structure, because the unsintered powder holds up the part, and you can stack parts in 3D space, and print huge batches at once. Now, this is a big one. It's metal PBF. A high power laser metal melts the metal powder, be it titanium or Inconel, you name it. This is the gold standard for rocket engines and implants, but it's tricky because it creates high thermal stresses. So you need heavy anchors to keep the parts from warping, and warping is a huge challenge in printing. The fifth one is binder jetting. Binder jetting, again, is all about speed. An inject head drops glue on the powder, creating a green part that you later bake into oven to turn into solid metal. And speed wise, it's 10 to 100 times faster than laser, and it's much cheaper as well. uh, DED is basically 3D welding. You feed wire or powder into metal pool. It's great for repairing expensive parts, like adding metal back on one turbine blade or building massive structures, right? So again, instead of replacing the turbine blade, you add metal back onto it. It's more sustainable as well, and corporation these get credit for sustainability, tax breaks and things like that. Now, material jetting is like your 2D office printer, but with plastic. And it creates full color photorealistic parts, sometimes even mixing hard and soft material in one go, right? It's huge for medical models. Surgeons can practice on realistic printed hearts. Now, if you need to go really big, you use WAAM, or that's called as wire arc additive manufacturing. It is a welding robot arm. It's low resolution, but you can print ship propellers and bridge structures, which is pretty, huge. Now, this is piece which is very exciting, which is printing buildings. And yes, we are printing buildings. Companies like Icon extrude concrete to build walls. The advantage of this is that it reduces labor and waste, and curved walls cost the same as straight ones. NASA is even testing this for habitat on Mars. And I'm going to take you through this insightful video.
This is now the world's largest 3D printed community. Lennar, one of the nation's biggest home builders, partnered with Icon, a 3D printing company, to build the community. 100 homes finished faster than it would have taken to build conventionally. This community, on the outskirts of Austin, was a trial run that took roughly 2 years to print. But the lessons learned here promise to make the process even faster in the future.
You can't learn that stuff in a lab. You have to get out here in the field with the weather, with the trades. You have to put it out there for customers.
Labor is lean and the cost of building materials is rising. 3D printing could solve some of that. Critical at a time when housing affordability is about the worst in history, and the nation is short roughly 4 million homes. Holly Feekings and her husband moved in just over a year ago.
Well, my son discovered it first, and he's a techie, and he was enthralled with the actual concept and the energy efficiency. And then we realized, it was really a safe home for 2 old folks. Single level, no stairs.
The homes are high-tech, energy efficient, wind, fire, and mold resistant.
This is significant improvement in evolving a housing market that has the ability to change over time.
This was an experiment for Lennar, and costs were slightly higher as they worked through the kinks, but Miller says he's all in.
The ability to adapt modern product to what we need for the future in housing, in building a healthier housing market, is amazing.
Wow.
Come on in. Welcome to our home.
Holly Feekings and her husband are retired. They've always lived in traditional homes, but they saw several reasons to try the 3D printed model.
What's great is there's no studs, so you can hang pictures and everything anywhere you want. You have to use screws to drill through the, concrete type wall, but it's been wonderful.
The homes here start at just under $400,000. That's about comparable to other larger homes in the area.
So what do you like, the most about this house?
Oh gosh, really the energy efficiency.
Feeking says her electric bill was just $26 in January, much lower when compared to the average bill for conventional homes.
You do have to run your air on hot days, of course, but it'll hold its temperature. You don't have to check the thermostat, and everything's automatic. And because of the construction, it really helps. It's very peaceful to live here.
And quiet, I imagine? Is it quieter?
Very quiet. We have a major road right out back and we don't hear it.
And that's the concrete?
It's the concrete and the insulated windows.
Icon and Lennar announced their plans to build this community in 2022. Since then, large-scale robots worked without a break, squeezing out homes like toothpaste, ultimately at the rate of 1 every 2 weeks. CNBC toured this construction site back in 2022.
Now we're on an active print site. So this is home number 6 in the queue. So actually what we do is we take digital, in any sort of standard digital software, we import it into our system we call Build OS, and it prepares it for robotic construction. So it will automatically do the structural reinforcement placing, the electrical outlets, the plumbing outlets, those kind of things. The promise of robotic construction is the promise of automation, reducing labor, therefore reducing labor costs. So right now, the minimum number of operators is 3. I think in the next 12 months, we'll automate the magma completely, so we'll be down to about 2. And I think the sort of holy grail is where one person can watch a dozen systems. You need one person to watch a dozen systems.
But as of now, you have 3 people building a house.
Which is not bad.
As printing progressed, ICON learned how to do it faster and with less labor.
The things we had to learn on this project that we had never done before were all the logistics of working at scale and the operations of fielding. I think at our highest moment, we had 11 printers out here working. And so figuring out materials delivery, shift changes, all the logistics of getting printers in the field, and then working in concert with the rest of the Lennar trades to lay foundations, print walls, have people come in and finish out the homes.
The partnership is unique because Lennar is such a large legacy builder and ICON is so new and so small.
This is really in its infancy. As you've said before, 3D printing, we don't see a lot of it. Why is a company as large as Lennar getting into this now?
So listen, we're just getting started. This is all about innovation.
How much will you invest in the technology and in ICON?
Well, we continue to invest in a variety of strategies around changing the methods of production, of construction, and we expect to take this all the way through. I mean, this is the first 100 homes, but we expect to be able to bring this to scale, and at scale, we really bring cycle times down, and we also bring costs down.
Completing the community was a learning process for both ICON and Lennar.
The biggest disappointment in the project was, the very painful learnings for about the first third of the project, where we were taking twice as long as we knew on paper we should be taking. Our costs were about twice as much as we knew they should be on paper. And so that was a little bit of a kick in the gut at the beginning, but you get out here, you work it out, and then by the end we were on pace and on target. And so we got there, but it was, you got to get out here and take your punches to learn the lessons.
What they learned here was a lot. They don't need the walls to be quite as thick. That'll save significant time in printing and money for concrete. They'll also move to a more open floor plan, reducing interior walls. Then they found a more efficient way to move their printers from model to model, which will also save time and labor costs.
For an industry that really hasn't changed at all in 200 years, in the last 2 years, we've seen an innovation that actually works.
But there's an important caveat. These homes are in an area that allows for faster building. In cities that have tighter building laws, homes may be more difficult to print. Other companies like Eden Homes, also in Texas, and Mighty Buildings and Emergent 3D in California are working on similar projects, but have yet to scale to this many at once.
Are these homes as profitable for Lennar as your regular homes?
Right now, they're not. They are mildly less profitable, which is fine. That's the innovation cycle. It takes time, it takes scale.
Lennar and ICON are already in the planning stages of their next community, just 7 miles away. It'll have twice as many homes, and they expect to bring them in at a more affordable price point.
Since we finished this community, we've internally had a whole redesign of our wall system to be even faster, even more affordable, and to even better integrate with the rest of the trades that have to work around what we do.
Ballard says they're still designing the next community, but the homes will be larger with a more efficient and much less costly wall system. They'll use the same printers, but he's already looking to new technology.
The next generation of printer is a printer designed to be able to print the entire envelope of the home, the foundation, the wall system, up to multi-story wall system, and even roof structures as the designs dictate. And we're very interested in looking with Lennar at these hurricane-prone areas, wildfire-prone areas, because all of a sudden you have an entirely resilient shell of a building.
I feel safer in this house than any house I've ever lived in. because it's so well built, it's not going to burn down.
If you look at the wind load in hurricane zones, the opportunity to build this home throughout the state of Florida, my home state, is amazing. In California, sadly, whether it's the rebuilding or whether it's just regular production, the opportunity to build using fire-resistant materials is amazing. We're at early stages with this, but as we mature, we think it can be a sizable part of our business.
Again, very insightful video. As you must have observed that we went from the G nozzle, which is an aerospace application, to the Adidas midsole, which is complex lattice structure, one size fits one, to printing buildings, which is a very different application. And essentially, what we are doing is we are challenging the status quo, right? How we perceive things and how things can be changed. This video is great illustration of how this construction industry, which hasn't changed for 200 years, is now changing and looking at ways, because not just because we want to produce something cool and fancy, but the need is that labor is expensive in Western world, and we have to find new and innovative ways through which we can manufacture and produce, uh, be it new parts or new buildings or anything which we need, right? The advantage of this was that it's fire resistant material was used. So in areas like California, where there is forest fire during summers, this could be really helpful. At the same time, it is energy efficient, right? The lady said that it holds temperature, so it's very sustainable as well from energy standpoint. So yeah, this is into insights into Icon and Lennar, which is a one of the big developers here in the US. So let's move to the next slide, right? So crucially, it is not just cheap plastics anymore. If you observe, we are getting into metals and what have you. We have moved to aerospace grade material. Sorry. Yeah. So we have moved to aerospace grade material. We are printing PEEK or ULTEM, which are frame retardant and carbon fiber filled nylon. That is as stiff as aluminum, but light and as plastic. For metals, we use atomized powders, microscopically spherical particles of titanium, aluminum, and steel, and this is the fuel for a revolution. Now, the challenger, right? Necessary evils, the support. One challenge is supports. As I mentioned earlier, you can't print in midair. If you have an overhang, you need to print a scaffold to hold it up. And in metal printing, these also act as heat sink. Removing them is a major cost. So we try to design parts that don't need them, right? So there are certain, again, challenges which comes with it. Now let's touch on the physics, which is where things get really complex. When you're printing metal, you have microscopic melt pool moving at 1 meter per second. And this is where success or failure happens. If it is too hot, you get gas trapped inside. And if it is too cold, the layer don't fuse and you get cracks. So as you see, temperature is the key parameter here, right? I touched upon this a little bit, the warping piece, thermal warping, which is, you see in a lot of different industries, PCBs and what have you. But in this particular area, The rapid heating and cooling creates massive internal stresses. Parts basically want to rip themselves apart, and that is why we have to heat treat them in ovens immediately after printing to relieve those stresses, right? So that becomes an added step, which is different than your conventional. Now, printing is only 50%, I would say. It is important to remember that it's just half the job done, right? You have to depowder, heat treat, cut the parts off the plate, remove support, at the same time, polish the surface. So the post processing piece is a huge part of this workflow, and it is, it takes some time as well and efforts. Now, speaking of quality assurance, question is, how do you check the quality? You can't use calipers on inside the lattice, right? So here, what we do is we use CT scans, just like what we see in hospitals, to look inside the metal for any microscopic pores or cracks. Now I'm going to focus on simulation and AI and the virtual printers, right? So even before you build a 3D printed part at a commercial level, you make sure that it's simulated. All the KPIs which are going to influence the part's quality, structural integrity would be tested virtually. And there are many commercial simulation packages out there. With the help of finite element analysis, you could, accurately predict the stresses, thermal stresses, and different parameters. But the challenge here is that it is computationally very expensive. It takes time, right? Which is, of course, currently done. However, enters physics AI. And what is physics AI? So, using neural networks to approximate the physics, essentially what we do is we take the historical data, simulation data, or test data. We create a geometric deep learning model based on the data we have, and then we test that with testing data, and then offer a new CAD or a new design to your machine learning model or geometric deep learning model, and you predict results faster based on the deep learning model you have built, right? Again, I'm going to give you a sneak peek on what that workflow is, and this is extremely revolutionary technology, which is getting a lot of traction, right? And let me play this video and give you guys more insights into
Okay,
this.
so hello everyone. To this chat, I will skip this. Simon already introduced the session, so there will be presentations from Lavanya. On my side, I will introduce briefly ALTER AI-powered solutions and mainly physics AI. My name is Diana Mavrutieva, and then we'll go through the presentation of Lavanya. So I think in the audience, we have mainly engineers, motor designers. Maybe you have already stepped in the area of AI, machine learning, design exploration, maybe not. I wanted just to give a quick introduction of what is the AI we talk about. And within ALTER, we have several solutions implementing AI and machine learning with three main goals to improve the CA processes and results by reducing repetitive tasks, allowing the possibility to make quick real-time predictions and to gain insight. So all this is exposed in different solutions with the same purpose to improve the CA process and to leverage AI. Like I say, it's not about replacing engineers by AI, but it is about empowering engineers by AI. So we have several products and solutions within our portfolio. Maybe you are aware, maybe not. I assume maybe many of you have heard at least HyperStudy for design exploration and optimization. And you are using this with Flux Motor to gain insight, to identify key parameters, optimize performances, and also making predictions, which is also machine learning, or first level of machine learning. I will not talk about HyperStudy, so the topic, the tool that you will see today in this presentation presented by Lavanya, the tool is Physics AI. And Physics AI is the further level in leveraging AI and machine learning to make predictions. It is based, it is about making real, quick predictions, replacing the solver, and leveraging existing data, geometry results that you have already simulated, and which can be leveraged to train a predictive model and be able to make fast predictions later on for new designs. Concretely, what it is about. So I have set here some images with motor design, but it can be something else. So basically what it is about replacing this approach that when we design a new motor, we have some requirements, we run simulations, maybe we are using optimization and we speed up the process. Nevertheless, we are running simulations, we generate some data to come up with a design. Now, this data that we have generated previously or data that we have available, we can use it to train a predictive model and replace the solver for next evaluation. So typically, here all these evaluations will be done in a much faster way. And at the end, the benefit for you as an engineer, as a user, is to save time and be able to make faster and better decisions. So this is what it is about. Physics AI is using geometric deep learning, so machine learning techniques that you are not, it's not compulsory to know exactly what it is about. What is needed to know is that Physics AI will learn directly from the geometry, the mesh, and the results. You can actually get rid of the parameterization if you don't have a parameterized model, but you have geometries, variants already simulated. You can directly use them to train Physics AI. The steps are really very simple in the sense that we are using the existing data, so the data available, to train Physics AI and then be able to make predictions. So those are the steps, whatever the physics or the analysis we are using. This tool is already exposed in other tools in HyperMesh environment. And it is solver neutral, so you can leverage Physics AI to make predictions with respect to thermal analysis or structural or electromagnetics, like here today in the example. So it is solver neutral. It is based on the data available and the results, the geometries and the results. And here we have some examples. Like I said, it's solver neutral or physics domain neutral. This is an example for a thermal analysis of HVAC system. So based on available designs and results, Physics AI model is trained, then it is tested. And for a new design, we can directly make quick prediction with instead of running the solver. And similarly, if we take an example of a bracket here, process is similar. Based on the existing historical data available, the model is trained, and later on we make predictions. Another one, and of course it can also be applied to electromagnetics. If we have data available to be used to train physics AI, we can make predictions for new geometries, new designs. So while the tool is really simple in the sense of what are the steps, you see, we start by importing the data available, then we train, we look at the accuracy, and we make predictions. So those steps are really affordable for anyone without specific knowledge in machine learning. But it is important to address some questions before you start using physics AI. To define the scope, what the model should predict, what is your expectation in terms of.
Okay, I'll stop the video here. And again, to summarize, this technology is physics agnostic and solver agnostic. So you could use any solver, any commercial solver available in the market, and any physics for that matter, right? The speaker in the video talked about electromagnetics, low frequency EMAG, but then this is applied to 3D printing, this is applied to modal analysis, noise and vibration, and different use cases across different industries. So again, the goal is that instead of going through conventional simulation route, you do, let's say, 10 different designs. You build a geometric deep learning model and then make your design space smaller and focus on 3 designs, let's say, out of 10, and then validate them using your traditional solver. So this is not replacing your traditional solver, but what it does is it augments and speeds up the whole product development life cycle process.
For the predictions, is it to
into the next slide, which is generative design, right? You also have generative design. Instead of drawing a part, essentially you tell the computer that here are the forces, here are the connection points, and the software grows parts organically, which often results into these alien looking parts, bone-like structure, but which are extremely efficient, material wise, structural integrity wise. Now, printers are getting smarter too, and they have cameras. I don't know, the picture here is not loading up, but they have cameras watching the melt pool. If it gets too hot, the printer instantly adjusts the laser power and it is self-correcting, right? So as we know, warpage is a big challenge. So the closed control loop helps here. I'm going to talk about the landscape and who is winning this particular area, right? So there is this Divergent 3D company, which is based in Southern California, and they have a cool strategy. They don't print the whole car. They just print the connectors, and they use printed titanium nodes to connect carbon fiber tubes. And this is the 3D printed vehicle. Again, not the whole vehicle is printed, but they print connectors. I'll give you a sneak peek. Won't go through the entire video, but we'll go through a sneak peek. And this is the car which Divergent built. It's called a Zinger 21C, and it's hypercar. And the beauty of this car is, like it has required zero tooling.
My energy bill dropped from $150 to $50 by doing this. My friends laughed at me when I spent $49.
All right, switch it up. Here we go. In the world. Now check this out. This is really cool. A lot of these parts here are 3D printed. So this specifically 3D printed. There are so many parts here that are actually saving on weight. And this car right here is performance based. First of all, let's have a look at what it looks like with all of this closed. Okay, look at this door. Look at this door. This is so ridiculous. I love it so much. Look how long it is. Just one big door. Kind of reminds me of like the Koenigsegg Gemera. They came out with this 4-seater hypercar and there was just one massive door to get into both the front and the rear seat. I just think it's so cool, you guys. Like, come on, and it's so lightweight. It's so cool. Soft door closed. Now this is a pre-production car, so we've got to be very careful with this. This is only one in the world, but I just wanted to show you like the front here, the front design. So look how massive this front lip is. It's crazy. And these headlights, this kind of front design actually kind of resembles an LMP race car. Kind of does, right? You've got the Zinger logo here. It's called Zinger because of the founder's last name. So his name is Kevin Zinger. Look at this baby. This is crazy. So this car has 1,250 horsepower, but get this, the weight of this car is 1,250 kilos, so it's a 1-to-1. So basically that means for every kilo of car you have 1 horsepower, which is kind of crazy, you guys. Like when you go 200 miles an hour, this actually has about 2,500 kilos of downforce just sitting here on the wings, which means in theory you could actually drive the car upside down without it falling, which is mad. Don't worry, it can support, just this, can support the weight of the entire car. So, let's just have a look at the back before we leave. So you've got the exhaust here. Now, talking of engines, we are looking at a twin turbo V8. Now, I'm loving the inside. Look how it's a streamlined, very narrow cockpit, right? So you can only have room for one driver here and a passenger behind you. If you don't have a passenger, you have room for your one bit of luggage. Here it is. You can get this customized with the car. That's pretty cool because there's no storage anywhere. Isn't that mad? And just look how wide this is. I was like, yeah, this is a cool car, but like, how do you get in? So there's a whole thing, right? This is how you do it. But on the 21C, oh, by the way, 21C stands for 21st century. That's the name of the car. This is a pre-production car. Some things are going to change, like the steering wheel. It's going to be slightly different. Also, all of this is pre-production, so this whole screen is going to change as well. So this is a real track-focused car. However, it is road legal, so you can drive this car on the road, but this particular version is very track-focused, so they want to keep it very like a manual look. You know, all of these that you can actually manually turn. Now, this is how you open the car door, like this. Boom, and then you lift.
I had a crazy idea. We were surprised that no one had done it before.
Success. So the body of this car is all carbon fiber, except for the parts that are 3D printed. So there's a bit of carbon fiber, titanium, and aluminium. Should we turn her on? Let's do it. Here we go. So foot on the brake, and then we just tap the stop button, which is pretty hard. Holy moly.
My energy bill dropped from $150 to $50 by doing this. My friends laughed at me when I spent $49.
Lucas, come on over. So this is Lucas, guys. He's the co-founder of Zinger, and your last name is actually Zinger.
It is.
Right? This car can run on lots of different fuel, right? So you can run it on just normal petrol, right? If you wanted
gas,
to, right?
yeah.
Or race fuel, right?
Or race fuel.
or zero emissions carbon recycled methanol. I was like, cool, sounds great. What is it?
So let's open the deck lid.
Okay, yeah.
And if you take a look on our actual fuel tank here, it says recommended M100.
I'll stop the video here, talking about what kind of fuel is recommended, but to step back, this is truly an engineering marvel. Again, as I mentioned, it's the connectors, right? Which makes it really efficient. This company's vision is to have a basketball size factory in which there are robots which are printing parts. And actually, this company works with OEMs, in Germany and across the world, and offer those 3D printed parts. And their Divergence vehicle business unit is Zinger. So Divergent 3D is the company. Moving on, this is desktop metal. It competes with casting, and again, using binder jetting to make million parts is cheap, but then bringing metal to office environment is what's in that video. Now, considering time, I'm not going to go through this video. We have another very cool application, which is relativity space. And relativity space is printing the entire rocket. Their Stargate printer uses robotic arms to print huge aluminum tanks, and aiming to go from raw material to flying rocket in 60 days. And this is extremely insightful, getting into the weeds of how this particular rocket was built.
My energy bill dropped from $150 to $50 by doing this. My friends laughed at me when I spent $40.
This is the world's largest 3D metal printer. It was built by Relativity Space, a startup that aims to print an entire rocket, including fuel tanks and rocket engines, in just 60 days.
I'm like looking inside a 3D printed rocket that is actually going to go to space. This giant hunk of metal. It's unbelievable.
This video is sponsored by Omaze, offering you the chance to win a trip to space. More about that at the end of the show.
There's a lot of UV coming off the welds. You can film it, but don't look directly at it.
You get sunburned fast, so it's like you're suiting up to go in a volcano.
All right, we're gonna go in to the 3D printer and see how it works.
All right, so yep, just hold this up, don't look at it. We are in the printer.
I can see it over there.
If we walk around here, we can get up close.
When you've got a classic ride, you need tools you trust. Whether you...
So that's the wire melting and the print head moving around. So that's the plasma discharge, and it's hard to tell, but it's doing things at every couple milliseconds. It's actually changing the electric waveform, which is how it's controlling the deposition so well.
Do you know the temperature of it? Like, is it just above melt temp?
It's just above melting for aluminum. Yeah, probably a few hundred degrees above.
The melting point of aluminum is 660 degrees Celsius, so the whole body of the rocket is effectively melted together one tiny bit at a time.
All the raw metal for the whole rocket that's printed is this. It's we kind of joke it's like Charlotte's Web, like a spider silk, but this is an aluminum alloy that's on a wire spool. We actually print about 10 inches a second. So this wire is really going super fast. And then the combination of lasers and plasma arc discharge are working to melt both of them together at the same time.
So where does the wire come out?
So it's right there.
Uh-huh.
And then the electric arc discharge happens right at the tip of the wire tooth.
This is a camera?
Yeah, that's a camera.
But why would you want to 3D print a rocket? Is it just because we can? It's funny to me that you had this experience with 3D printing where you're like, oh, 3D printing is clearly the future. Whereas I feel like a lot of people's experience with 3D printers, as mine has been, it's like incredibly frustrating. I feel like 3D printing is that thing that seems like it should be great, and yet whenever I try it, I don't get a result that I'm happy with.
Yeah, I know. I can tell you, we had plenty of experiences the first couple of years where we ended up with a pile of metal and it didn't work.
But there are actually good reasons to 3D print a rocket. A rocket has 4 major systems: payload, guidance, structural, and propulsion. The bulk of the rocket is made up of the propulsion system, including the propellant tanks and the rocket engines. Cryogenic fuel and oxidizer are pumped through an injector into the combustion chamber where they react, releasing an enormous amount of heat. This causes the exhaust gases to expand, exiting the rocket nozzle at high velocity. The faster this exit velocity and the higher the mass flow rate, the more thrust that can be generated. So rockets are huge, complex engineering projects, which up to this point have largely been manufactured using traditional techniques. That means before you can build the rocket, you first have to build the tools to build the rocket. For example, to build NASA's next huge rocket, the Space Launch System, or SLS, they first needed to construct the Vertical Assembly Center, or VAC. This is a 170-foot tall tool for welding together the domes, rings, and barrel sections of the rocket's fuel tanks.
They built that like an aerospace thing, and they've had to spin up all these custom tooling designs and validate that those work before it actually starts building the rocket. And they've finally got one being assembled on the pad after 11 years of development.
My energy bill dropped from $150 to $50 by doing this. My friends laughed at me when I spent $49.
In contrast, Relativity Space, the company, is just 5.5 years old, and they plan to launch their first rocket this year.
I see this as a like old engineering style versus Silicon Valley style of build something, figure out what's wrong with it, and build another thing that fixes those. Right? The difference is I've always done that with software. These guys are doing it with aerospace hardware.
So this is the actual rocket tank structure of what we're going to be launching to orbit at the end of this year. So this actual thing is launching to space.
That will go to space.
This will go to space, and it's by far the largest 3D printed product really of any type ever made that's going to fly. I think maybe of any type in the world.
But it still looks 3D printed, like you can still see the layers.
Yeah,
right?
You can still see the layers. It only adds an extra 5 to 10% of the mass with the roughness. When you actually cross-section the material and look at the machine parts of it, it looks like normal metal. Like actually at this end, this is printed as well. We just machine it afterwards. So it looks like normal metal in the joint sections.
Does the surface roughness cause any aerodynamic problems?
No, none at all. Yeah, it's actually the exact same aerodynamically. This whole thing, we simulate the print before printing, because if you just printed the 3D file and said press print, you would end up with a printer that's warped and like material falling all over the place. It wouldn't actually work. So we've invented software that reverse warps the whole part before printing it. So the robots are actually doing this really wobbly, weird shape, but then it's actually perfectly straight within a human hair across the entire length. As it cools,
the warpy thing turns into the...
And we simulate all of that. So it's a big computational solver that simulates it. And there's many, many other problems we've had to solve to actually get printing a rocket to work. But it's all these little pieces over the last couple of years. And we've really started to hit some breakthroughs, which is also why now you see a whole rocket. Yeah, you can step up here actually if you want. Yeah.
Hello! I'm like looking inside a 3D printed rocket that is actually going to go to space.
Yes.
This giant hunk of metal. It's unbelievable.
Yeah.
There's like rings inside.
Those are printed in stiffeners, and so those help prevent the rocket from buckling and crumpling. So if you had a Coke can and didn't pop the tab, if you try to step on it, it's almost impossible because there's pressure inside that keeps it from buckling. But then when you pop the tab, there's no pressure and you can crunch it super easy. It's not hard at all. So rockets are the same. The 50 PSI of pressure, which is about the same as a car tire, keeps it inflated and keeps it from crumpling. But then those stiffeners also help keep it rigid. Yeah, so believe it or not, a rocket tank is thinner versus its diameter than a Coke can. So when you look at a Coke can, you know, how big it is and then how thin it is, a rocket tank is actually thinner than that. So yeah, it's pretty light. It has to be very light.
Sure.
When you've got a classic ride,
Aerospace companies started using metal 3D printing over a decade ago to construct small, complex parts, for example, the injector.
That is the most important part of any rocket engine, where you're basically got to take the liquid propellant and turn it into a fine mist that mixes really rapidly. And those have actually been transitioned to 3D printing all over the industry.
Traditionally, something like this, it's a rocket engine injector, so it mixes liquid oxygen and liquid methane propellants together, and this is what actually produces all the fire and flame that is in a rocket engine. Traditionally, it would be over 1,000 individual pieces, and it would take 9 months. But here, we're 3D printing the whole thing in one piece. It takes 2 weeks, and it costs 10 times less.
One of the big benefits of 3D printing is reducing the number of parts. Have you ever thought about how inside a rocket's combustion chamber, it gets really hot, up to 3,500 Kelvin? That's hot enough to melt virtually any metal. So how do the combustion chamber and rocket nozzle not melt? Well, the answer is they're cooled by passing the cryogenic propellants over them.
On the Space Shuttle main engines, I love to talk about them because inside those engines, it's hot enough to boil iron. On the outside, you can freeze stuff to the exterior of this because you're running liquid hydrogen through these things. But to make those, you basically had to take thousands of very small pipes, and then you would form them into the shape of the combustion chamber and the nozzle, and then you would braze weld them together. And this was a ridiculously labor-intensive task. You would have 1,080 individual pipes running up the side, all having to be welded together to make the combustion chamber and the nozzle on the Space Shuttle engines. So you can actually 3D print these things.
This is a rocket nozzle being 3D printed, and you can see the channels for the cryogenic propellants being printed right into the single part, instead of having to add 1,000 pipes on the outside. Smaller parts like these are typically 3D printed using metal powder and lasers.
So you can see the cooling channels are all being built as the one piece. So this is a nozzle. It really just lays down a layer of powder that's about 1/20th the thickness of a human hair. So it's really, really fine layers, just over and over and over and over relentlessly for probably about a week or so, and then out comes the rocket nozzle. All printed as one piece. It's way cheaper than traditional. And this has 4 lasers going at once.
That's amazing.
I get asked a lot, well, aren't 3D printed metals not very strong, or how can it actually work? But the printed materials are stronger than they would be built traditionally. Actually, it's counterintuitive.
It is.
Because we develop our own custom alloys in-house. So we have a whole material science team just developing our own alloys for 3D printing. And the fact that it melts and then cools and solidifies very, very quickly.
My energy bill dropped from $150 to $50 by doing this. My friends laughed at me when I spent $40.
You can take advantage of that physics principle to get really strong alloys.
Another major benefit of 3D printing is that it allows for rapid iteration. You can build a part quickly, test it, and then redesign rapidly and print again.
So this is a version of the engine that's about 3 years old at this point, but what's amazing is when you actually look at the engine design today, it looks entirely different than this. So each version we build, we can iterate and make better. So that's the other, when we say software-driven manufacturing, that's really what it is. Since you don't have fixed tooling, all the part geometries are just controlled via the CAD model, and then the printers just print, direct from file, essentially. It means you can actually change the design extremely fast. So building a whole engine only takes us about a month. So then a month later, you can do a better version, and a month later, a better version than that. So this particular one will actually be, I believe, one of the first flight engines that's actually launching to orbit on our first rocket.
So this tubing, not 3D printed, right?
Not today.
Okay.
And the future versions, we're actually, integrating that into the printed housings, and we're going to have a way that that's all printed too.
Perhaps the biggest impact of the 3D printing approach could be to totally transform what a rocket looks like, With 3D printing, engineers can build parts that would be impractical or impossible with traditional techniques. Smooth, curvy, bio-inspired designs are just as easy to print as ordinary structures.
This is actually part of our next rocket, Terran R, so it's even larger.
This is like the base of a tank?
Yeah, so it's gonna go out, it's almost done printing, it's gonna go out about to here, so it's 16-foot diameter, but it's almost like a shell.
I was gonna say, like, this reminds me of suddenly we're in The Little Mermaid or something.
Yeah, it's just for stiffness though.
It's not that you plan to make it bio-inspired, it's that that structure is actually the optimal structure.
Yeah. We're actually designing many features in the rocket that could not be manufactured unless it was 3D printed, which is one of the secret sauces of why you had to build a whole company around it, is because our rocket actually looks entirely different 3D printed than it does traditionally. Like, in my mind, it's been more akin to like gas internal combustion engine to electric. Really, people are trying to put batteries and electric motors into existing products for decades. Like, everyone knew electric vehicles were the future, but Nissan and Ford had really not compelling products for a long time. It wasn't until a company came along, called Tesla, that decided, well, actually, the shift to electrification means the batteries, the electric motors, the factory, the design of the product, how we're actually going to scale the company, the supply chain, all of it's different because of electrification. I mean, that's in some ways the dirty secret of electric cars and why they're able to be automated in production, because the part count is so much lower. So for a fully 3D printed rocket, we have 100 times fewer parts, which is what we're guiding to. There's no fixed tooling in our factory at all, unlike the rest of aerospace that's still really 60 years later, even since Apollo, building products one at a time by hand with hundreds of thousands to millions of individual parts. And no one's really changed that paradigm of how an aerospace factory actually fundamentally works. Yeah, this is the new...
When you've got a classic ride, you need tools you trust. Whether you...
fully 3D printed rocket. So yeah, we'll have dragonfly wing type structures, and we're building it still, but that's the first one, and then that's that one for scale. So yeah, it is definitely bigger. Yeah, so our rocket is named Terran 1 and Terran.
Again, considering time, I'll pause this video here, but just to recap, as you saw, for such big rockets, you need those VSCs, right? Support even before you can start manufacturing it. Custom tooling, it is labor intensive. There are shapes and parts which are difficult to use lathe and CNC on. So those are challenges, and with traditional manufacturing for certain areas. And then we'd also discussed the benefits. So rapid iteration is one of the benefit, where you want to fail fast, right? If you are manufacturing something, you can't wait for it to manufacture for, let's say, a long time. It takes a long time, and then you work on it and realize that this is not what you want. This is not based on for your design, or have quality issues and things like that. So rapid iteration is a key piece here.
And then our 3D.
So another company launcher, but before that, I want to focus on the previous slide actually.
This is the world's largest.
Where I missed this. What relativity space uses is DED, which is directed energy deposition. This video is old, and old meaning like the company is 5.5 years old, maybe now 10 years old. It's a startup based in California, and they use directed energy deposition method for 3D printing those rockets, Terran 1 and Terran R, right? Now, speaking of their success, were they successfully able to launch? The answer is no. These guys were not able to achieve a successful orbital launch with their rocket. But mind you, the reason of the failure was not the 3D printing. Actually, it was a key achievement. The rocket's fourth stage performed very well, and it successfully passed max Q, which is the maximum aerodynamics point of stress, validating the structural integrity of 3D printed design. And it was the first 3D printed rocket and first methane fueled rocket in the West to reach space, passing 100 kilometers Kármán line, right? Where it failed was the second stage ignition that has more to do, with the physics aspect than the 3D printing aspect. So it was a great success from 3D printing standpoint. Launcher, again, it's a vast company, another startup which is working in this space, 3D printing, and really making a lot of waves. I won't go into detail of this, so we'll skip to Aerojet Rocketdyne, and they took this legendary space shuttle engine, printed a key component called Pogo accumulator, and they eliminated over 100 welds. Similar again to GE, where welds were eliminated, and cut the cost by 35%, which is holy grail for every corporation out there. SpaceX, of course, the Super Draco escape engines on the Dragon capsule are fully 3D printed Inconel material, and these are the first printed parts to fly human to space, which is again revolutionary. Skieki uses electron beam to print massive titanium parts for submarines and wings, and they deposit 25 pounds of metal an hour, which is huge. And it's drastically cheaper than machining down a giant forged block. Again, won't go through this video. Now, one of this, a killer application for additive manufacturing is heat exchanger. As we know, heat is a big problem, and we need to find innovative ways to dissipate it. Of course, heat exchanger is traditional, but then the design here, we can print incredibly thin walls with massive surface area, making it 50% smaller and then twice as efficient. Now, we have seen, again, a lot of wings and wheels, but then the real challenge here, or rather challenger here in this field, is in medical revolution, right? What 3D printing is doing. On dental side, there is a company called as AlignTech, which produces Invisalign for orthodontics treatment for braces, and they are formed over 3D printed molds. They are again at the top of innovation cycle, and they print around 500,000 aligners every day for orthodontics treatments, which is another application. For implants, companies like J&J and other companies as well, they use titanium hip cups with trabecular surface structure that bone grows into. So it's a hip implant in this case. Similarly, for hearing aid, 99% of hearing aids are now printed to fit patients' ear perfectly. So it's again, customized, similar to the Adidas midsole. Now, this is a big initiative, maintenance, repair, and operation, and it's overall it's all also about repair instead of throwing away a worn turbine blade, which I mentioned earlier. We use DED today to print new metals onto it, extending the life of expensive asset and making the process more sustainable. Now we are moving towards a digital factory where printers are connected to cloud. There are robots which are harvesting parts, and there is powder, recycling powder to be sustainable as well. The economic verdict is AM is king for low volume and high complexity. Traditional manufacturing still wins for simple, high volume stuff, but that's the win zone for printing is expanding every year. So that's a great, way to look at things here. Now, to give you landscape summary, we have covered different startups. We have covered, Titans as SpaceX, GE, and then we have also talked about OEMs, right? So that's the industry landscape. What's the future, right? And what are the challenges? So we clearly need new engineers. When I say new engineers, is that we have skill gap. Engineers today are taught to design for drills and lathes, and we need to teach them to design for lattice and lasers. The hardware is ready, and the workforce needs to catch up. We also have certification problem. We have 100 years of data of steel forging, but only 10 years on printed steel. So regulators are cautious, be it FAA, FDA. So the industry is working hard to build shared material databases. The, the big question is, are we at the Star Trek replicator stage yet? The answer is no. It's still complex, but we are closer than ever to the dream of push button and get parts. With that, I conclude my presentation. And thanks again for listening, taking your valuable time. I hope this was insightful, and I would love to take any questions you may have.
Yes, sir. Thank you, sir. Ajinkya Shetty, sir. Now, participants, you can unmute yourself and ask questions.
Hello, sir. Am I audible?
Yes, you're audible.
Yes, sir. So first of all, thank you very much for giving us idea about that broad scope of the 3D printing, and I will be happy if you share all the playlist of the YouTube, because it is very helpful while teaching the 3D printing course to the students, so we can give the idea about the various case studies. Okay.
Absolutely.
So my question is, as I saw in the most of the videos, like the General Electric, and also you show the most of the video. In most of the video, there is a one point is there, when we prefer the 3D printing, the number of parts get reduces.
Correct.
Okay. So what I'm thinking means, I'm thinking in in terms of the maintenance. So most of time, what happen if there are large many of a parts, then if there is a damage get happen, we only replace that damaged parts, right? But if in the 3D printing, if we are making a whole object as a one piece, so in the maintenance point of view, is a costly 3D printer is a costly option or not?
So that's a great question, first of all. As you know, you rightly mentioned, there are several parts which are stitched together, right? Now, I do not have data per se, industry data, on where it would be more expensive to replace that part. But considering 3D printing is lot cheaper than your subtractive or CNC lathe traditional one, I would think it would still be cost effective because there is no tooling required, right? But again, I do not have data on that, but that's a great question, right?
Okay, sir. Thank you.
The parts are more durable as well. So that's something we have to take into account. And it's used mostly where the parts are mission critical. So with more durability, you kind of get more life as well to that part. And then there is also aspect of typically the designers, even though we see one part, the designer often print modular subsystems as well, not the entire assembly. So that helps too. Does that answer your question to some extent?
Thank you, sir. Now,
Yeah.
any other question?
Hello.
Yeah.
Hello, sir.
Hello.
Sir, I am Dr. Prashant.
Hello, Dr. Prashant.
Sir, I have one question. You have shown certain videos related to 3D printed rockets, related to that. So, what about the quality assurance and consistency, sir? Because there may be porosity or surface roughness that may weaken the rocket. So, in this regard, how the certification is carried out related to this thing?
Correct. That's a great question again. So again, the post processing takes care of the surface roughness, but then um, the video which we went through, one of the videos which was relativity space, the CEO did mention that the surface roughness in that particular application was not causing any aerodynamic issues, right? But then there is a definitely big challenge where the metal additive manufacturing isn't perfectly uniform. So that's definitely a challenge. But then how that translates is into regulators and challenges is something to be considered as well. But then post processing eliminates all these defects, right? There are non-destructive testing to verify the integrity. Then there is something called as HIP, hot isostatic pressing, to close internal pores. And then heat treatment is also used to normalize microstructure. Of course, there is machining done, right? So there are certain areas where you don't need that kind of finishing, and it does not affect um, anything structurally. But certain areas you kind of post process with the methods which I mentioned, and yeah, that is a way to go there.
Okay. Thank you.
Is there any
There is
other
also
question?
CT scan and things like that, right? In one example we mentioned, there is CT scanning industrial X-rays to map internal pores, and things like that.
Okay. Thank you.
Okay, if there is no further question, I thank Ajinkya Shetty sir. Sir, thank you very much for delivering such an informative session where you have shown that where the world is going for 3D printing, how we can increase the effectiveness of heat exchangers and can increase the efficiency of various machines through your talk. So thank you very much, sir.
Yeah, thank you again for your valuable time and contribution, for actively participating, and I appreciate this opportunity. And I can share the presentation as well as the links so that it can be helpful for
Yeah.
the budding engineers.
Yes, sir. Yes. Thank you very much. So
Thank
we'll
you.
share that presentation with participants.
Yeah.
And thank you, participants, for actively participating in the session. We will meet tomorrow at 2 o'clock for the uh, 11th session, which will be delivered by Dr. Abhishek Patange. Thank you very much.
Thank you.
Yeah.
Thank you, sir.
मला पण बसवत नाहीये रे.
आपण जेवलो नाही का?
जेवलो तिकडे जाऊन तू आणलेलं खाल्लं.
नंतर जेवलो नाही.
हा?
नंतर जेवलो नाही. चला, काय जेवायचं?
पोळी आणि भाजी आहे.
भाजी कसली आहे?
फ्लावरची.